Hey there. Hello. This feels like 8 o'clock in the morning. Is it two? What's that? Okay. Okay. All right. This feels like 8:30 in the morning. I can see Craig in here teaching college physics one. Maybe there's like a demonstration with the president of the university on a tricycle. Anyway, uh, thank you all for coming. We are welcoming people from near and far, and we really appreciate seeing you here to celebrate Craig Kletzing and his work. I've enjoyed being a colleague of Craig's since he arrived here at the University of Iowa. And also my office is on the 5th floor too, and we had lots of opportunities to talk about teaching, including how he did get the president to get on that tricycle. I asked him last summer, and how did you get that? He said, well, I asked him. Okay, I guess that's a lesson for us all, right? Anyway, teaching, we talked about the university, politics. We'll talk about that later. The best choice of instant lunch to eat at your desk, where to get tacos in San Diego, and all kinds of other topics. And so he's greatly missed here, as you all are sure to know. And I hope you'll all introduce yourselves to, if you don't know her already, to his wife, Jeanette Welch, who's here today and who will be at the reception later tonight. Okay, so let's see. We have a great program here, and we've got the talks this morning, tours in the afternoon. You'll hear more if you haven't heard it already, and then the reception and meal tonight. I'd like to thank the organizing committee, the committee of Greg Howes, Allison James, David Hartley, David Miles, and Steve Kepler from Clemson. And I'd also like to thank Heather Meinert and Sierra Hutchins for all the work that they've done to make this happen. Thank you. Thanks. Let's thank everyone right now. I'd also like to thank the college and the university for their support of the department and the support particularly of the space physics group. And so we have some representation here from the dean's office, Josh Weiner, Associate Dean Josh Weiner, Roland Resfikis, and Chris Cheatham. And also we have the support of the Office of the Vice President of Research and Ali Salim. So thanks to all of them. And so even though we know that Perky outside the lobby says that we have a universe without bounds, I'm going to introduce Scott Bounds to MC the program. How many times have you heard that?
Oh, I've heard it a lot lately. Jeff has it plastered on his door next to my office. I'm sure Van didn't know that I would be joining the department when he said that. Okay. Oh, I need to get my presentations started here. Hello, computers. Sorry. Okay, so in a way, I feel like this is almost the most important presentation I've ever made in my life. I know much of what I'm about to say comes as no surprise to anyone here. We all knew Craig well. Craig was a wonderful person to work with, collaborate, and just to talk to. Oh, sorry.
Switch it so that they see the.
Oh, just see the presentation. Okay. Sorry. Too busy giving my talk. Craig was selfless with his time, easily approachable and quick to share, whether it be wine, a thought, or advice. He was never pretentious. While he was my boss, our relationship was more as colleagues and friends. I know this to be true for everybody who worked for him. And you will hear very similar sentiments from my fellow speakers today. Since the following talks are going to cover Craig's research, involvement in research, I'm going to focus more on his life and share a few of the stories that Craig told me or the memories that I have. There are too many memories for just this 20-minute talk, and everyone here has memories that are just as important as mine. I'd like to encourage everyone here to share their memories and their stories of Craig as we gather this afternoon and this evening in remembrance of him. I would enjoy hearing. I loved hearing stories about Craig. Craig had a very interesting life. It's a perfect way to honor Craig, as he enjoyed sharing his stories and experience with everyone he met. Next slide. Wait a minute. Oh,
We'll get
more technical difficulties. There we go. Okay. Most everybody knows Craig was born in Sacramento, February 3rd, 1958. Craig's father was a lawyer who worked for the state of California Department of Water Resources. His father was blind from an early age, afflicted with the same condition that impacted Craig's vision. His father was president of the National Federation of the Blind from 1961 to 1966. So Craig had some lofty shoes to fill. While Craig had a desire for science and particularly physics, he also had an appreciation for the arts and, as we know, music. In high school, he worked as a stagehand and had a knack for lighting. There are multiple stories here about his stagehand work, but there's not enough time to share all of them, so I will defer for later. For some of his innovative lighting design work, he won a scholarship to Berkeley in theater, which he took advantage of, but physics remained his goal. He graduated with a degree in physics from Berkeley and went to UC San Diego to get his PhD. Carl McElwain was his official advisor, sort of a link back here to Iowa. He worked closest with Roy on his sounding rockets, and Roy's going to talk a little bit later. There are many more stories here, particularly about the rocket launch for his thesis rocket, but I'm going to let Roy have that. It was at San Diego where Craig met Jeanette. Craig had just come back from an extended vacation in Hawaii and was a bit cash strapped. To save money, he was hitchhiking, and Jeanette stopped to pick him up. The second time she saw Craig hitchhiking, she did not stop to pick him up. Though, to be honest, her car was full. She had another passenger and she had her base in the back seat. Two passenger. Okay, sorry. They would soon meet up again as Craig was rooming with a couple of music majors. Another link back to his interest in music. And they invited her over to the house there, and Craig and Jeanette would properly meet. And on December 31st, 1987, New Year's Eve, they got married. Around 1987 or so, Roy would move to the University of Alabama, Huntsville. Craig would travel out to UAH in the summers to work with Roy while he was still getting his degree. The first summer, he drove all the way from San Diego to Huntsville in his car that did not have air conditioning. he learned a lesson that you don't drive around in the summer in the South without air conditioning. In 1989, he and Jeanette moved to Huntsville, spent just under a year there. In one of life's little odd twists and turns, this was the first time my life actually crossed Craig's life. I was an undergraduate at UAH at this time from 87 to 91. Though we walked around in the same halls in the same building, I never met Craig. Before the end of 89, Roy moved the group up to University of New Hampshire, where Craig spent a couple years there. Craig also spent 2 years in Garching, Germany as a visiting scientist at Max Planck. Because he and Jeanette wanted to have all their musical equipment in Germany, since they were going to be there for 2 years, they took the unusual mode of transportation across the Atlantic, a Polish freighter ship. Spent nearly 2 weeks on a trip going down the coast of the US and then over to France. And this was during the Christmas holidays. In 96, Craig was hired here at the University of Iowa, a tenure track position, and reached full professor in 2005. Craig received many awards here at Iowa. These are just some of the major ones. Of particular note, the Don and Marie Garnett Chair, and became a fellow of the American Physical Society. So I'm just going to touch on one sounding rocket here. Craig's first sounding rocket was the race rocket. This is where I first started working for Craig. I was hired in 1999 to work on this rocket and in collaboration with the UCLA Large Plasma Device experiment that he was running. Race was my first collaboration. Race was the first of many collaborations Craig had with Jim LaBelle, and Jim's going to talk about the rockets here a little bit later, but I'll leave all the details for the rockets for Jim to share. I've just collected here many pictures of Craig through the years. This may even be him lecturing in this very hall right here in the center. Craig worked on many projects, as you will hear about from my fellow speakers. I do want to share one story. This is the one story that if you said, tell me a story about Craig, I'll tell you this one. And I don't know why this one comes to mind. It's an odd story. So in the upper left of the images here, you see a picture of the UCLA Large Plasma Device, or more affectionately known as LAPD. They had big LAPD logo on their doors. This is a project which Jim Schroeder will detail more later, so I'm going to leave more of the details for him. But Craig and I were building instruments to be installed on the LAPD, and we would get 1 week out of every 6 months to go out there and do the tests on the LAPD. So there was a very narrow window to get out there and do these, and they would pass it along to the next group who wanted to run experiments. So we had that short window. We needed to travel out to LA to get as much data as possible as we could get in that 1 week. On one of these trips, and we were traveling out there, this was pre-9/11, pre-cell phone. I had already gone up to the airport. We were both traveling on the same flight. But Craig would always work in his office to the very last minute. And he had it timed to know when he needed to leave the office, whether that be, grab a taxi, or oftentimes Jeanette would come pick him up and drive him up to the airport. I'm sitting in the lobby area waiting to board the airplane, and they started boarding, and Craig's nowhere to be seen. And they board, and they're boarding, and they're boarding, and Craig still hasn't shown up. I started worrying about, do I get on this flight, go out and run the experiments, needing to call Craig, hey, what do you want to run? Or do I wait? Because I was Craig's ride from the airport to the UCLA campus. And so I'm starting to fret about, do I stay? Do I get on the flight? They're down to a handful of passengers remaining to be boarded. And of course, 10 minutes before the flight, they close the door. So I'm really starting to panic here. And lo and behold, I see Craig nonchalantly walking up the terminal. And he says hi, and I turn and grab my stuff and start walking behind him. And he goes straight up to the counter. And of course, in those days, you had to have your boarding pass. And his method was always to go to the counter and get the boarding pass, not go to the ticket counter, go to the gate and get the boarding pass. And as he's walking up there, I think, okay, now the agent's got to come over here and print out his boarding pass. But as he walks up, the agent says, "Hey, Craig," grabs his boarding pass, scans it, hands it to Craig, said, "Have a nice flight." At this point, my jaw must have been on the floor because this is premium service. We get on the flight. Craig quickly stows his bag, pulls out his headphones, his New York Times paper, sits down, headphones on, starts to read the paper, all before I'm past him and to my seat. So Craig really knew how to travel, and he traveled well. So speaking of Craig's travels, not only did he travel well, he was well traveled. By our accounting, he hit every continent with the exception of Antarctica. I know some in here have been to Antarctica, but he went to Greenland for his rocket launch, so someplace that one of these places where very few people get to go to. He and Jeanette actually did one of those around the world tickets where you leave from one coast and return on the other coast. I also list a couple of his favorite spots that he went for vacation, and I'm pretty sure you noticed the pattern. He loved the beach, particularly blue water beaches. He went to most of these locations more than once. I wear my favorite Aloha shirt today in his memory. I got this my first trip to Hawaii after Craig said, "Hey, you should go to Hawaii." And enjoyed it. I've been there 3 times since. The wine. I don't have a picture of Craig with a glass of wine or a bottle of wine. But I think we all know he loved his wines. At least once a week, a box would show up in the department mailroom with Craig's name on it. It was filled with wine. We would joke that this is Craig's booze. Craig's booze had arrived. Most importantly, he loved to share with his friends his wines. It was for sharing. I'll never forget, during one get together for the group, Craig opened a rather rare bottle from the Baca Valley. To put it simply, it is the best wine that my wife and I have ever had. To this day, we rave about it. And I'm very grateful that Craig and Jeanette shares that with us. I'm going to close with, we all know Craig loved music. I have a list of the names of Craig's band and some pictures here. You know, Craig enjoyed playing his guitar in his leisure time. He was in many bands through the years. The one I never knew about was the One Night Band, where apparently a bunch of Craig and Jeanette's friends got together and jammed for a night, and never got together again after that. Fork in the Road, the last band, which is the one on the top there, still is playing. And for those that are in the area, if they're interested, Fork in the Road is playing June 27th and July 7th. So if you get a chance, July 27th, sorry. Typo. July 27th. I'm sorry about that. Jeanette also wanted me to mention that Craig bequeathed his favorite Larrabee acoustic guitar to Logan Steffens, who is a member of Truffle Peg, which that's Logan right there in the lower picture. um, of truffle pig playing together. I'm going to close the way Craig would close many of his presentations. I'm sure lots of us remember presentations from Craig where he would have, "That's all, folks," at the end of his talk. I want to thank you for letting me share my memories with Craig, my boss, colleague, and friend. Okay. All right. Now I'm going to switch over to being MC. All right. So first up, first off, one of our presenters, Arya, had some flight troubles, and we'll get here a little bit later this morning. So we're going to move his talk to the very end. But next up, we're going to hear from Roy Torbert. Roy, are you on?
I hope so.
Okay. All right. I'm not sure.
Share screen.
Okay. You're going to share, Roy?
I don't know. Whatever you want to do. She has my slides. I can do whatever you want to do.
Okay. I don't think we're hearing Roy on the.
Can you hear me?
All right.
I can hear you. I'm just not on the loudspeaker.
Okay. All right. Try again, Roy.
Yes, I'm here.
No. Okay. I'm not hearing it.
I hear him on here, but I don't hear him.
Yeah.
I am unmuted according to the.
Yeah, we can hear you on the computer here at the podium,
Okay.
but we're not hearing you on the speaker system here. So we want to make sure everybody can hear you. Does it need to be one of those?
This one here.
Okay, can you try again, Roy?
Yeah. Are you there?
Awesome. Yeah, good.
I don't know if anybody else can see me, but I put video on for a little bit just to assure you that I'm not an AI.
Do you your slides so you can share your screen so it'd be easier for you to tap through the slides?
So it would be better for me to share?
Yeah, so you can tap through the slides when you want to.
Sure. No, that's fine. Let me see. Share. Let's see. I'm going to share desktop 2. Does it come through? Oh, wait a minute. I have to punch another button.
There you go.
There you go.
You
All
should
right.
see a picture of Craig.
Yes, we see that. All right.
Okay. Should I go? I should go here full screen somewhere.
Yeah, go full screen.
Which is down here.
Yeah, there you go.
There we go.
All right. Take it away, Roy.
Yes. Well, first of all, let me say my regrets for not being there, and in my present condition, it's not advisable to travel. But I'm assured by doctors I will be, well, not as good as new, but in fine fettle in about 2 or 3 weeks. So I'm honored to talk about Craig. Scott, I appreciate you letting me have some thunder on some of the things from Craig stories. But Craig was my second student at UCSD student. First was Pat Newell, and both of those students, but in particular Craig, made mentoring graduate students so easy. I deluded myself to say this is going to be a piece of cake. Craig came down to me. I remember, I think it was in '81 that Forrest Moser, whom he worked with at Berkeley, called me up and said, "Look, I'm sending a student down to you. He's a really excellent student. I want you to take good care of him." And so he sent down, as Scott said, technically he was Carl's student. I was research faculty, research scientist at the time. And but Craig and I did the whole, and he did his thesis on my rocket project. So as we all know, Craig is is just a very friendly, collaborative person. And as a student, he was always engaged. There was never any question about pushing him to do anything, as we all know. And it made working with him on rockets just so easy. It also helps, in addition to being intelligent and motivated, to be lucky. And Craig was lucky. So this is a story about Craig when he was about 2 months old. And I think Jeanette's in the audience, so she can correct me. I don't know if many of you know that I believe Craig was the very first human to be treated in the Stanford Linear Accelerator. His father, as Scott mentioned, was not born blind, but they were born with a family trait in which a very, as I remember, a very virulent cancer is in the optic nerve, and if not, the nerve wasn't removed within a short period, it would go into the brain. And I'm not sure, but I think Craig had an older brother who was in the same situation as his father. I'm not sure. But it was, as Craig related to me, Stanford Linear Accelerator had come online just about that time, and they determined that they could that it would be safe to save one eye with the radiation, but not both. And maybe you don't know that he really didn't have the use of the other eye his whole life. So I know we all remember him staring down over papers with the use of his eye, but probably nobody knew the difficulty he had with his eyes, and he just carried on as usual. That's characteristic of Craig. So the next piece of luck has to do with the next slide, which I have to do, right? Do I do it? No, this way? Yeah. Okay, so I picked this paper, which came out of his thesis, was basically electron time dispersion on this rocket flight. And this rocket flight was out of Sandstrom from Greenland. And you'll see in a minute some other comments on this paper because it has an interesting connection. So it turned out that we were doing electron time dispersion. And this is an electron spectrogram of the full flight. Can you see, now that I'm doing it, can you see my pointer? Can anybody see my pointer? Is anybody there?
Brooke?
Can you see my pointer?
Yeah, Craig, we can see your pointer.
Okay, great.
Can you hear me?
I don't know if you can see here that they were all through this flight. These electron time dispersions going through multiple arcs, flying from Sun to Stromfjord. And over here is in this period, there was some interesting ones, which we'll see in the next slide. And I just wanted to put up the abstract here. In the thesis, we worked on one model of how to fit these dispersions. But, it's characteristic of Craig that he and I were not really sure that this was the right mechanism of these electron time dispersions. And I'll comment about that in just a minute. Let's see what happens when I push this button. Okay, so that's a blow up of that time. And you can see these electron time dispersions here from Craig. And Craig's thesis was working on the distribution functions, which you see off here to the right, which I've collected up to model these dispersions, which are caused by accelerating electrons. So the faster ones, the higher energy ones arrive first, the small ones. Very much like what we were trying to do in that flight, which I'll describe in a minute, with ions, but we couldn't for a very interesting reason. So let me tell you a little bit about that. So the reason I picked this paper not only comes from his thesis, but it has to do with this flight. Okay, so this was in Greenland, and it's flown in an earlier flight, 1974. That was my thesis, and also in association with Gertz Poschmann, who, were he still with us, I'm sure would be in the audience. He was very friendly with Craig and a great mentor for him. Anyway, this story about this rocket you probably heard, but has to go along with the luck that Craig had. So Craig almost didn't get his thesis data. We would have had to got it from somewhere because of this rocket flight, which was in 1985. It was to be flown 1 minute after Chuck Carlson's flight. There were two rockets. The 1 minute was as close as they could get. They were going to go together, very much like, I believe the name is Trice, as Steve Fuselier can mention out there in the audience, but of course also a preface for tracers. So it turns out that didn't quite work. At the time of the launch, there are various actions that have to occur in the last 60 seconds before launch. So Chuck's is going 1 minute later. We are supposed to go 1 minute earlier. And there's some functions that have to go. You have to go to internal power. You have to uncage the gyro. You have to arm the upper stages of those rockets. And so it turned out in a way that probably caused fright to quality assurance people that before T-minus 60 seconds, the guy who armed the upper stage said to himself, didn't talk to anybody, outside the countdown says, doesn't matter when I arm these stages, I'm going to arm the stages. So he armed the stages, upper stages. And incredibly, the guy who's supposed to uncage the gyro said the same thing to him without talking to the other guy. Said, doesn't matter when I uncage this gyro, I'm going to uncage this gyro. I'm not sure that internal power, I'm not sure that internal power might have gone off before T-minus 60 seconds, but in any case, it was on internal power at T-minus 60 seconds. And interestingly enough, the guy that was on the gun sight, that for these rockets going off fast, that you have to have a gun sight to track the telemetry, otherwise you lose it and you're out there trying to find telemetry. Anyway, the guy who did that said he had a dream. He had a dream that this rocket was going to go off early. So it was Greenland in the middle of winter. So he suited up and went out to the gun sight and was sitting on the gun sight. And sure enough, at T-minus 60 seconds, the guy arms the first stage and the rocket takes off. Pandemonium in the blockhouse. But it soon became clear, well, upper stages are armed, the gyro's engaged, and it's on internal power, and the guy's tracking telemetry. Because there was a frantic conversation with Chuck Carlson at the time. Do you go to launch a minute early? And Chuck says, look, I got my countdown. I've got to go when I got to go. So unfortunately, there were 2 minutes between the time that Craig went and the time that. But due to this set of circumstances, Chuck got his thesis data. And I would say that's about the luckiest I've seen in a space science experiment. The other thing on this slide is you see, as Scott mentioned too, when we wrote this paper, which is somewhat later. Oh, let me mention about the results. I should have mentioned these characters that Craig, we pondered those results. And there's a paper later, some number of years later, which a much better explanation, still with the parallel electric fields, but the parallel electric fields in kinetic Alfvén waves is a better explanation of those electron time dispersion. Anyway, it also says here that he was on leave to Max Planck Institute for extraterrestrial physics. And this is the time period he spent with Gertz, and he and I and Gertz worked on at the time of this paper, we were contemplating cluster, and we worked on a low altitude version of the electron beam experiment, which we flew on Freya. Not very successfully, but at least it was an interesting experiment to try to do. And during that time, Craig developed that thing and got interested in the electron drift instrument, which of course I was working on with Carl earlier on, and then led to the Equator S experiment, and then the which Craig worked on, and then of course cluster. Maybe weren't so lucky on cluster 1, but cluster 2 at least worked fine, and then on MMS. So I'm sure that there's going to be a lot of people to talk about RBSP and then called Van Allen probes, now Van Allen probes, and other programs with Craig. So in interest of time, I'm going to skip to MMS. And the next slide, if I come up here. Okay, so for those of you who don't know, the electron drift instrument on MMS is really a rather remarkable instrument that a lot of people worked on. Carl, myself, Jack Quinn, who was also a graduate student at UCSD. Götz Poschmann, of course, was the PI on Cluster, and Scott worked on MMS. And this is a cross-section of that instrument, which is really quite complex. It has an electron gun up here, which has to be well calibrated. And that electron gun shoots out a small electron beam in a particular direction, which you must find so that it goes 1 gyro diameter, or 1 gyro radius, an orbit 1 gyro radius of electrons, and comes back in to these optics. And it goes through these optics. It's steered by a whole collection of electrodes. I'm pointing at them here into an energy analyzer and then onto a microchannel plate. And there's a whole bunch of electronics back here and a down here a thing that computes how to get that direction, which is not easy to do. Okay. Anyway, it's a rather remarkable instrument, and Carl McElwain worked on these. So the gun was the property of MPE. These electronics are on Cluster were our part on at UNH. This part here of the microchannel plates was from Lockheed Martin when Jack was at Lockheed Martin before he joined us in New Hampshire. And these optics, which are really quite complex, were originally the task of Carl McElwain. However, we had some real difficulties with Cluster. It still worked pretty well. There were a lot of things we didn't understand about those optics. And by the way, part of it is this screen, which has to be highly transparent. I'll show you in just a minute how that screen. Anyway, when we went to MMS, it was Craig and Scott and Chris Sigsbee, I don't know if she's in the audience, who took over these optics for MMS. We had all this stuff back here from UNH, and the gun part had been transferred to Graz under Baumjohann and another engineer, Rumi Nakamura. But these electronic optics, which were really the problem that we had on Cluster, became Craig's and Scott's effort. And here's some pictures of those optics as they were. I took a little picture of the University of Iowa. It was attached to that. Here are these optics. There's a cone down in here, buried down in here, the microchannel plates and stuff. And you can see the grid that had to be done. And this is before we mount the gun on here. Scott can maybe relate many stories about getting this grid right, which was a totally new way from Cluster. But more importantly, this is the thing about Craig, he in the laboratory, by both simulation, which Chris worked on, and in the laboratory, Craig really tackled on what was really going on with these optics. And that made the success for MMS that this was so well done that we didn't have any of those problems. And remarkably, even though we had other problems with this instrument, it was only supposed to last 2 years, maybe 2.5. The electron gun part has lasted 9 years, which is a remarkable accomplishment. And I wouldn't show you all the trajectories that they calculated and all the tests that they went in the laboratory to confirm, which was really a major accomplishment. But it just points out that Craig was an all-around scientist. He never left anything undone. And it was a real pleasure to work with him on doing that. I think I have a picture. I believe that's you, Scott. I think that's you holding some of the optics from MMS. Is that right?
I think that might be Rich.
It might be Rich. Okay, I can't remember.
Yeah, it is Rich. So
okay.
yeah, Rich worked on it.
Okay. Anyway, there are some of the optics. You can see some of the pieces out there that that they did, and they to make this this is the inner analyzer cone. You can see the serrated edges, and the coatings with that were all new type, and everything else that Craig did that made that instrument. And that instrument has been a significant part of MMS's success. Not only can we measure electric fields reliably in the inner magnetosphere and a whole bunch of inner magnetospheric models on the electric field and MHD modes in the inner magnetosphere, but it actually calibrates the double probe and the magnetometers that make it the MMS success. And so that was a major accomplishment on MMS. I've probably taken up my 20 minutes. I just wanted to hit a few highlights. So I'll be glad to take any questions, but I'll just stop there and say, what a guy.
Yeah. Okay. Thanks, Roy, for sharing. I know Craig's rocket launch, thesis rocket launch is always a good story to share, particularly in the sounding rocket community. Okay, so as I said, we're going to slide everything up. So the next presenter is going to be Dave Hartley. Dave Hartley, who is here at Iowa.
Well, I better stop sharing.
All right, yeah. There is, but since Aria is going to be late, we're going to. Oh wait. Oh, you're right. Don't slide up just yet. Okay. So we're going to take a break. I'm slightly out of order here. So we're going to break for 20 minutes, and then come back at 10:20. See if we can figure out how to. Okay, can I get a quick check from everybody online or somebody online that you can hear us now? Whoops. Can we see the chat or something?
Yes.
Yes, now. Okay. All right. Great.
Yeah.
Okay. Thank you. All right. So we'll go ahead and get started with the next talk. Hey. Quiet children. Okay, so our next talk is going to be David Hartley, who is a researcher here at University of Iowa. Has been working here with Craig or worked here with Craig for a little while, and I will hand it over to Dave.
So is that close enough? Should I get a little bit closer? Is that loud enough? Okay, cool. So it's a great honor to be able to talk today to try and honor some of the memories of Craig that we all have. And yeah, I hope I can capture some of that in the talk that I'm going to give today. So I came to the University of Iowa in 2015 to work with Craig on the Van Allen probes mission. And so I've been here nearly 10 years. And so have a lot of great memories of interactions with Craig over that time in kind of various different capacities as him being a mentor, friend, colleague, all of that stuff. And so, yeah. So Craig was the PI, the principal investigator for the emphasis instrument on the Van Allen probes mission. The Van Allen probes was launched into the heart of the radiation belts to try and understand the variability of the radiation belts. And I'm sure everyone in our field will agree we've completely solved that problem now. As is the way with science, you kind of, the more you learn what you don't actually know. And so that's kind of where we are, I would say, with that research. And so the emphasis measured the electric and magnetic fields in the radiation belts, and those interactions between particles and waves kind of drives a lot of this variability in the radiation belts. And so you can see on the left-hand side, there's magnetic and electric field spectrograms. There's a whole kind of zoo of different types of plasma waves that you observe, and particle interactions with all of these different types of wave can cause acceleration of the particles, losses of the particles, and a whole kind of zoo of different responses. And so that's kind of the essence of what the Van Allen probes mission was trying to uncover and solve. I want to show this slide mainly because it highlights how many people got to work with Craig on the Van Allen probes. This is looking at a whole, searching for co-authors of Craig's with papers that include the kind of keywords RBSP, Van Allen probes, or emphasis. And, there's a lot of different people. I think many of the people in here are in this room as well. And yeah, it really just highlights how broad Craig's impact was within our field. There's lots of people here from all over the world who got to work with Craig during the Van Allen probes mission. So my first interaction with Craig was at the GEM conference in 2014, where he was like, oh, just come and sent me an email saying come and hunt me down and we'll get lunch together to talk about this work that you've been doing, which was what would ultimately make up the last chapter of my PhD thesis. And I remember as a grad student approaching the PI, the instrument PI of a NASA mission, being quite daunted by that prospect. And Craig was, in a group of people who far more important than me. And I kind of went up to him. He's wearing flip-flops and Levi's jeans and, extremely chill guy. And he cut off all of the conversation that he was having with far more important people to come and talk to me. And I think that is a testament to who Craig was as a person. And the kind of weird comment about Levi's jeans, I know he wore Levi's because one AGU conference in San Francisco, I'm fairly certain he'd been there all week. But the only time I saw him at AGU was in the Levi's section in Macy's. So that's how I know he wore Levi's jeans. So after this lunch meeting with Craig, we had a lot of emails back and forth, and it was nice kind of looking through all of my old emails with Craig to dig out things. And he sent me an email saying he was quite interested in having me work with him as a postdoc. And so I won't get too deep into science, but the kind of general premise of this work was to test an assumption used in previous works where you could calculate the magnetic field wave power from the electric field under a whole host of different assumptions. And I only mention that because kind of over the years, I can still trace back a lot of the work that I've been doing to that one conversation that I had with Craig in GEM in Portsmouth, Virginia in 2014. And so just to kind of go through very quickly the kind of thread of this, the first thing we did was remove a different assumption on that calculation between E and B. We've then gone through and studied how that assumption, how good that assumption is as a function of different parameters, namely frequency and density, kind of revealed that this structure was consistent with a known impact on the electric field instrument where it might not measure exactly what you think it's measuring. And we've kind of been working through that even up to today. And that's something I still work on. And so, yeah, it's interesting that you can kind of trace everything back to that one meeting with at GEM. So a bit more of experience of working with Craig. I know Ari is not here yet, but his talk is, I know he has the big man in his talk, and we used to refer to Craig as the big man upstairs because he was our big boss man, and his office was directly above us. So yeah, it's not a God complex. Working with Craig, it was always interesting when I was telling him that I was going on vacation, because I think most of the time I never actually got to telling him which dates I was going to be away for, because he was much more interested in where I was going and if he could offer recommendations for things to do or restaurants to go to. So yeah, from that aspect, it's great when your boss doesn't care when you're not going to be there. Yeah, so I've had many great conversations with Craig about numerous topics, food and music. My favorite music conversation with Craig was when I told him that I was going to a Taylor Swift concert. Yo, Swifties, yeah. And then the next day he asked me how the Shania Twain concert was. So I don't necessarily think that Taylor Swift was within his music remit. Another kind of, I guess, semi-interesting thread is how often those conversations would lead towards Costco. I don't know if he earned some form of commission or something, but it was amazing how often you'd be having a conversation and, the cheese at Costco or the wine at Costco or the glasses at Costco were really good. And yeah, that's kind of a fun memory. Yeah, Craig, I think, is a great colleague and mentor to many of the people who are here today. If he gave you advice, it was generally worth listening to. I can't think of that many occasions where he gave me direct advice, which made it even more kind of pertinent when he did. thinking back to Scott's story earlier about the airport, I think one of the pieces of advice he gave was that if you haven't missed a flight, you're spending too much time in airports. I think another piece of advice was to never have a television in the bedroom, because the bedroom is good for two things and a television is conducive to neither of those things. Maybe that's not the right time to be sharing that one. And yeah, I mean, even, you know, I think about a week before he passed, actually, when I went to see Craig, he even then was giving me career advice when clearly he had so many other things that he could have been thinking about. And I think that's testament to who he is as a person, or who he was as a person. Another note is that he was always really approachable, as you know, we all know. Whenever he was in the building, his door was always open, but that's only kind of part of the story. I have a kind of silly slide that I put together about the different outcomes of trying to see Craig. And so when you'd go upstairs and try and find him in his office, the first situation you could come across is that the door's closed and he's not there, probably because he's in Tahiti or something. And so the only way you could follow up then was to send him an email. And I'm sure we all know that Craig was not great at replying to emails. I'm sure he read them, because the number of times I'd say to him, "Oh, I've sent you an email." And he's like, "Yeah, I know." And I was like, "Well, what's the second half of that?" The second situation you could find yourself in is that Craig's door was open, he was there, and you could have a great conversation with him about, you know, physics or Costco. And for someone who was always so busy with so many different things, he was so generous with his time when you could catch him. And I can think of times where, you know, I'd been struggling with some physics issue or something, and you know, I went into his office. It must have been about 4:30 on a Friday, and I was like, "Oh, I just really need to talk to you about this." And he, you know, we hashed out things on the chalkboard for kind of 2 hours, and it turned out we meant the same thing, but our ratios were the wrong way around compared to each other. So that's what the confusion was. But yeah, I don't know why it took 2 hours now, but yeah, he was always so generous and willing to talk to you. The third possibility is that his door was open and he was in there with someone else, and so he was busy chatting with, I guess in this case, Scott, who Craig looks happy and Scott not so much. But in that situation, you could either wait outside for what could be quite some time or come back later. And then the fourth possibility was that his door was open, but he wouldn't be in there. And that could lead to, I guess, almost two other possibilities, where you'd walk into his office to see if he was there, and he'd emerge from the bathroom behind you, which is kind of a strange interaction to have. But also, even if he wasn't in his office, you could often track him down through his kind of distinctive deep voice in the halls of Van Allen. So even though you couldn't see him, you could hear him and sense his presence and hunt him down that way. I kind of joked that I would come up with real statistics for these at some point over the past almost 10 years. But yeah, I didn't do that. And so the little caveat that these statistics may in fact be made up. I'm going to talk just a little bit about some of the science that I know Craig was excited about. And so these plots are from a talk that he gave at AOGS in 2017 from work with Iva. And the general premise was looking at the direction of energy flow of a certain type of plasma wave. And if you have more energy going towards the equator than away from it, that's indicative that the waves are losing that energy in the equatorial region and passing it on to the particles, which is a method of heating. And so that's what the kind of blue regions on these plots show. And there was a whole range of different assumptions that kind of went into calculating how much of that energy goes into the particles. But this work showed that this kind of energy deposition from His waves can kind of be an important mechanism for heating the plasmasphere, with some events reaching quite high kind of heating levels. Another thing he was excited about was this radon transform. He would often start talks by saying, "Who here has heard of the radon transform?" And the more times he gave the talk, I think he was more disappointed that more people were raising their hands and that it was less kind of a new exciting thing. But the general premise, it was kind of to, you have an image, you look along the image at different angles. And, in here we can see a kind of rising tone chorus element. So when at the angle that you're kind of looking directly along that chorus element, you see a bright peak. And that's a way of extracting this angle or the sweep rate of the chorus elements. And I know Craig liked this work a lot because it was not a normal way of looking at things from a physics perspective. It was work with Ananya Sengupta in the electrical and computer engineering department. And he liked it because it highlighted kind of new ideas and approaches that you can get from collaborations with kind of new people that you don't normally interact with and different departments. I wanted to show this slide mainly because I remember at the Van Allen Probe's Science Working Group meeting, I was looking through all of the talks and everyone had these very specific kind of talk titles relating to different areas of Van Allen Probe's research. And then Craig's title was just something interesting. And you can read into that two ways. One would be that he genuinely thought this was just a really interesting piece of work and he wanted to present it. The other way, and maybe it wasn't this, but finally time for something interesting as opposed to all of the same talks that we hear at all of these meetings over again. Yeah, I don't know which one it was. I don't know how I'm doing on time. I'll keep going. Okay. So this slide is just to highlight the high levels of data quality from the emphasis instrument. This was, I think, probably the last first author paper that Craig wrote talking about the science data and how to use the data. And I know this was kind of an important point for Craig because he absolutely hated the thought of people doing dumb things with his data. And yeah, there's multiple occasions where that may have happened. Probably some of it from me. Fortunately, I could speak to him about it before publishing anything. But yeah, he really wanted high quality data and people to understand things that they were doing with the data. And so there's a nice section, mainly written by, I think, Andre, in that paper, talking about the wave normal directions and how to appropriately use them. It also has a section on the sheath corrected electric field, and I wanted to mention that not just because that's what I did, but during COVID, we had weekly Zoom meetings it was me, Craig, Iva, Andre, Ivana, and Bill to talk about this electric field issue. And I think Iva and I recently went back through all of our notes for those meetings to look for loose threads. And there's like so much good science that we did that kind of got done a little bit and then left behind because we were kind of in a bit of a time crunch to try and get things done by the time the Van Allen Probe's money ran out. And so it's great that, that was one of those anchor meetings during COVID that it was really great. There was great science with great people, of which Craig was a big part of that. And yeah, I just wanted to point out the high quality data from basically the entire Van Allen Probe's mission from emphasis, with greater than 90% coverage for the survey mode data. So Craig was extremely generous I have a lot to thank him for. Not just, he's the reason I'm here today. He gave me my first postdoc position, kept me on as a research scientist, offered huge amounts of help with multiple applications for visas and my green card application a few years ago. And yeah, I'll be eternally grateful to him for all of that support and the opportunities that he had given me over the years. And yeah, his kindness and generosity will be missed by many people. And then I have the same finishing slide as Scott, but slightly less. Yeah.
Thanks, Dave. All right, so now we have reached the point where Arya would have talked, but we have heard Arya is on the plane. So fingers crossed he gets here by the end of the presentations. So we will bump Jim LaBelle up. And so I will say, take it away, Jim.
All right. Okay, so Roy talked about how lucky Craig was, but I actually feel that I'm the lucky one because my career happened to dovetail so nicely with Craig's that we became partners in rocket experiments for 8 different rockets spanning about a 20-year period. And so I've over that time spent a very much time, had the pleasure to spend a lot of time with Craig on the phone writing proposals in various science operations centers, calling the rocket launches, and of course adventures all over the world, sometimes with Jeanette together. So very nice. I wanted to, let's see. All right. Is it not on there? Oh, that's it right there.
This one?
The second, that one. So I was going to say, so we collaborated together. Well, Craig and I were partners on 8 different rocket experiments, and there were a lot of papers and results that came out of those that are all part of Craig's legacy, including, for example, the TRICE rockets, which spawned the TRACERS satellite mission that many of you are familiar with. But I wanted to focus on one particular contribution that I think illustrates. Yes. So I was going to focus on as the title. Whoops. Maybe this one works. Is there a way to advance it? Start the slideshow, maybe. Can we go full screen? Oops. Get rid of this. You know how to get rid of that. Oh, excellent. Thank you very much. Okay, so out of all the different results that came out of these sounding rockets that are part of Craig's legacy, I wanted to focus on the correlator, the wave correlator experiment, because this is something that I think so illustrates, Craig's abilities as an experimentalist. And as the title indicates, the thing about the correlator is that it's a probe of the detailed plasma physics. It's a way of basically squeezing out of nature the very basic elements of plasma physics, the interaction between the particles and the fields. The 2 publications I mentioned here, both Kletzing papers, are the 2 go-to papers. Like if you want to learn about the subject of correlators, students, these are the go-to papers that you go to, the 2 Kletzing papers there. Now, wave particle correlators could be done with any plasma wave in principle, but Craig recognized the advantages of working with the Langmuir waves or high-frequency plasma waves. And the advantage of that is, first of all, they're very common. If you fly a rocket to above 600 kilometers in the aurora, you'll see hundreds of them. And also, although they're structured, very often one single frequency component is dominant. That turns out to be kind of critical for the technique. And then finally, the particle bunching is relatively easy to observe. I mean, in fact, there are many papers out there where these waves have been observed, not with the fields at all, but directly with particle bunching. So that these are the ingredients essentially to do a wave particle correlator.
Hey,
So-
hey, Jim, excuse me.
Sure.
Yeah, we're not able to see the slides on the screen.
Okay. So everybody has that now? Okay.
Got it now. Thank you.
Okay. All right. Great. And now it's not advancing. Whoops.
Actually, first.
I'll get manually here. It's not. Oh, make sure you're in there. Okay. Great. Okay. So sorry, we're getting off to a rough start here. So I wanted to show here. So Craig Kletzing, together with Laurent Muschietti, actually wrote the seminal paper, the best description actually of the theory of the wave particle correlator, which is based on prior work by Muschietti, built on that. But what's shown here is the result for the simplest case, which is the case of a finite, a short wave packet and low amplitude electric field in the wave. And in this case, you can actually directly solve for the perturbation of the electron distribution function by directly integrating the Vlasov equation using unperturbed particle trajectories. And so the results are shown here. What you have on, this is for a downward coming wave packet. The right-hand panel shows the wave potential, the potential in the waves. And you can kind of see that it's a packet because the waves get smaller towards the bottom. This is the downward going wave packet. The left-hand panel shows the electron distribution function. And so this is in phase space. So physical distance is on the vertical axis and the velocity is on the horizontal axis, with the middle being the resonant velocity, the velocity at which the electrons match the, whoops, not getting the, here we go. The velocity at which the electrons match the phase velocity of the Langmuir waves. And so what you see here is that as the electrons start to feel the effects of the wave packet, you can tell that they're bunched here. What's shown here are contours. The gray are excess of electrons, and the white are deficit of electrons. So you can see the electrons start to get bunched basically in the field of the wave. And if you look closely, the electrons that are close to the middle point, the resonant electrons, they're actually their phase is 90 degrees out of phase with the wave potential. And so these electrons are actually in phase with the wave electric field. So these electrons are actually being actively accelerated or decelerated by the electric field. And this component of the perturbed distribution function is called the resistive component. It's the component that is being actively accelerated or decelerated in the field of the wave. But what you can notice is if you go a little off of the resonance curve, off to the edges, you can see these kind of droop down a little bit. There's a component of perturbation, bunching of the electrons at the electrons that are just a little bit off of the resonance that is actually in phase with the wave potential rather than the field. And so these are not exchanging energy. These electrons are not exchanging energy with the wave. And so you have, that's called the reactive component. So you have basically two components of these perturbed electrons. The resistive one, which is peaked at the resonant frequency, okay, and the reactive one, which occurs to the sides, off the resonance. And the reactive one is particularly difficult to measure, particularly challenging to measure. The resistive one goes one direction, so you can catch it even with a fairly broad energy band. It's relatively easy to catch. But the reactive one is quite easy. If your energy resolution isn't good enough, it's quite easy to miss it. It can be washed out. So the theory paper that these guys did, they also did the case of, as you can tell, if you go up here, as the electrons penetrate deeper into the wave packet up here, you can see that the bunching is getting stronger and stronger. And so to deal with longer wave packets or larger fields, you have to do a nonlinear calculation or a simulation, which also shows reactive and resistive components. And if you go to the case of a very long wave packet where the electrons pass through the wave packet for a long time, you actually have this situation where it settles into a pattern where the electrons are essentially trapped in the positive potential well of the waves. And so in this case, you only see the reactive component of the perturbed electron distribution function. So this theory paper really laid out the predictions, the detailed predictions for what needs to be observed by a wave particle correlator instrument. Now, I should say there had been one correlator instrument that had been published and done before Craig came along, and this was Bob Ergen's paper at Berkeley, but it observed in the aurora, it observed only the resistive part, which would be consistent with being the short wave packet weak field case. But what was really being needed was to see these other parts, the reactive parts as well as the resistive parts. And so Craig took it on himself to design an instrument that could do that. And I just wanted to point out some of the innovations that Craig put into this. So one was the choice of the particle detector to use. And that's shown here in this slide. Craig shows these things, they're called bagel detectors, okay? They may not look like it, but it turns out if you open one of these up, they look like a bagel, actually a sliced bagel, okay? With the sliced part facing outward towards us. And the idea is the particles come in on the outer part of the bagel here, and if you bias the voltages just right on the outside and inside of the bagel, the particles of a selected energy will make it through the bagel and be detected. And the beauty of these bagel detectors is that they have you notice the area, the collecting area is quite large because your collecting area is all along the outside of the bagel. So it's a huge area by standards of particle detectors. And so you get floods of particles coming in. This turns out to be critical for getting a high time resolution with a correlator because you have to sort these particles by phase and so forth and still have enough for good counting statistics. And you want to do it all within a millisecond or so. So that was one advantage. The other advantage is these, you'll notice right away, these are looking up from the spacecraft, and the spacecraft is aligned with the magnetic field. So you're catching the very particles that are parallel to magnetic field that you want to get to correlate with the Langmuir waves. And the second thing you can notice is there are quite a few of these bagels, 8 of them to be exact. And so Craig could place, each one is dedicated to a different energy, and Craig could make these energy spacings quite tight. So you could really try to pick out, have sufficient energy resolution to pick out that reactive component that sought after to verify the theory. So the other innovations, I just wanted to highlight a couple of other innovations that Craig made, because I know he's quite proud of. He came up with the idea of locking an oscillator to the wave. So the wave field comes in off of the wave antenna, and you lock an oscillator to it. And his idea was to use a divide by 16 in the loop with the locking. So the idea is you lock the wave, the natural wave, not to your oscillator frequency, but to 1/16 of it. And so what you get is as shown here in the bottom panel, you get a square wave that's locked to your wave, but what you really have as your running oscillator is 16 times, a square wave with 16 times that frequency, and also locked to the wave, to the natural wave. And so you can use that to sort the particles into 16 different phase bins. This gave phase resolution that was unprecedented in this. The previous correlator had only quadrants or something. So this was an innovation. Craig also put some innovations into how he latched these data in. So of course, using careful baseline restore, so you get a symmetric waveform, that's critical. And then he basically turned this latch open on the upward swing of the signal, and then clock the data out on the downward turning. And so that way, that assures that you get exactly the same time for counting particles coming in for every phase bin. And that's very critical, because if you had even a slight difference in the time allotted to each phase bin, that would manifest itself in a fictitious correlation. So these are some of the, and Craig also had a number of other innovations that I can't go into in detail about this latching process and how that worked. The calibration, of course, was a whole story in itself. And so let me go straight to the results here. So this was the first rocket, aptly named the Rocket Auroral Correlator Experiment, launched in 2002 from Poker Flat. And this shows the waves. And you can see that they're highly monochromatic, okay, which is just what you need. You could imagine you could lock a square wave signal onto that quite easily. And that's in fact what the instrument succeeded in doing. And there were many examples during this flight of correlations, and some are shown here. Okay, so what's shown here is each panel here represents 1 millisecond of data, and for a selected energy. Okay, and then the horizontal axis is the 16 phase bins into which the particles were sorted. And the way Craig came up with to analyze this was that he plotted here on the vertical axis is plotted the standard deviation of the counts in each bin, relative to the statistically randomly expected, right? You expect to get an equal number of counts in each bin. And to the extent that you get more or fewer, you can calculate the statistical significance of that. And that's this parameter sigma on this axis. And so what you're looking for is high, extraordinary high numbers of counts in a given channel, more than would be counted by chance. And you can see that in a few cases here. I think I have, this slide will advance. I guess I have to come down here. You can see a few examples here where that happens. And so over here, for example, you have a case where you have several 2 sigma results in a row, which is equivalent to like a 3.5. And here you have 2, 3, or 3.5 that are equivalent to like a 4.5. So these are statistically very unlikely to happen by chance. These represent correlations. And notice the angle here. They're close to 0. This is with the wave potential. So they're close to 90 with they're between 0 and 90. So they're kind of a mix of reactive and resistive, kind of just what you expect from the theory, actually, for the short wave packet. So this was the race experiment. And based on that, another experiment was planned, because you always have a chance to improve the results with the next experiment. So the next one was called CHARM. The CH stands for correlations of high frequencies. And in this experiment, there were many dozens of correlations, but I show this one. This is the poster child. Okay, what you have here is a electron spectrogram. What you see here is one of these dispersed electron features that Roy showed, that Craig was so instrumental in investigating in his early years. So this feature here, and then down below you see six different energies. Okay, each panel here is a different energy, and for each energy you have the phase bins along the vertical axis, and the color indicates the significance, the statistical significance of the counts in there. So when you see blue, that means there's a surfeit of counts. When you say red, there's a deficit of counts. And what you can see here quite strikingly is these extraordinary correlations, right? And they follow exactly the pattern. Right, so you start with 390 EV, you have a striking correlation. Then as the energy decreases, you see at 320, decreases further, you see at 260. This is a kind of data plot that brings tears to the eyes of experimentalists. And by the way, these show a very clear signature of reactive, because they're dominant at 90 degrees, and that's 90 degrees to the field. So this is a classic case of a strictly reactive case, which is the difficult one to measure. And so let's see, how am I doing for time? Do I have a few minutes? Couple of minutes. Okay, I'll just mention that we saw a whole lot of these correlations on this rocket, and many of them were resistive rather than reactive. And there was a very interesting trend that was noticed that's sort of illustrated here, for example, in this bottom one. So here you have a correlation. And notice that the correlation is in a different place in the phase bins than the previous one. So this is a resistive rather than reactive one. And here you have another one. And notice that this one is what we call red over blue. So this is where the electrons are feeding energy into the wave. And this other one is blue over red, where the wave is feeding energy into the electrons. And the red over blue comes on the leading edge of an electron beam, and the blue over red on the falling edge. And that's kind of a consistent pattern that we see. So that's an interesting observation and with Craig's instrument, and has a possible explanation. I'll just show you the cartoon of it up here. If you imagine that you start an electron beam at some very high altitude, going down the field lines, the high energies will outrun the low energies, and you'll end up with a situation where you have a highly unstable distribution that leads to a burst in the growth rate of the waves. And then, on the other end, where the beam turns off, the high energies disappear first before the low energies, and you get a steep negative slope, which leads to damping. So you get this is a kind of model here, a test particle model where the growth rate's been calculated based on a model of injecting the beams, and you see this burst in growth rate and burst in damping at the end, and that's kind of consistent, makes it for a plausible, not definite, but plausible explanation for what was observed with Craig's instrument there. So I think I'll finish here and say that, this is just this instrument. What I find remarkable about Craig is that he had so many different legacies. So, he worked on, the dispersed electrons. He worked on the Van Allen probes, MMS. He was all made contributions in so many different areas. But this is one of them, is this wave correlator area. And he really made a substantial contribution. The main papers in this area are due to him. And, the work goes on, as I say, and I'm sure people will build on his work. And I just leave with a picture here of us in one of the Rocket Science Operations Center, where we spent many hours, staring at plots like that, trying to figure out when to launch the rocket. So thank you very much.
Yeah, well, that's fine. Thanks, Jim. All right, so we're going to move on to another Jim, Jim Schroeder, who was a student of Craig's, worked on the work that I alluded to earlier, the large plasma device, and I will hand it over to him.
Great, thank you. That's it? That's it? Okay.
Can we verify those online can see the slides?
Get rid of it. Great.
Okay.
Okay, thanks. Good morning. My name is Jim Schrader. I'm an assistant professor of physics at Wheaton College in Illinois, just a suburb of Chicago on the western side. I was a grad student here at the University of Iowa, and like others, before I dive into the science, I'll offer some stories about Craig. I'm here, my assignment is to talk about Craig's studies of Alfvén waves using the large plasma device. But first, story time. So Craig was a member of my thesis committee, but that really doesn't capture the role that he played in my time as a graduate student. He was more like an informal advisor for me. And that's because I spent a lot of time in his office. Craig was committed to people. And one of the ways that came through is that he was relatively easy to find. When he was in the building, as Dave noted, his door was usually open. And unless somebody else was in there, he was willing to be interrupted. So several times a week, I'd be in his office asking questions. And that time of discussion would evolve into talking about restaurants or music or editorials in the Times. And I wrote in the acknowledgments of my thesis that Craig was either extremely generous with his time, or I've been failing to get the hint for 6 years. And Craig came up at the end of my defense and said there was no hint. You weren't failing to get a hint. So he was committed to people. He was also committed to doing science well, as others have noted. And I got to see that firsthand by traveling with him to the large plasma device several times a year. 3 or 4 times a year, we'd go out there, and I'd get to spend several days working side by side with Craig, which I thought was a really special experience. Now, looking back on it, I appreciate it. And the reason is that I think a lot of grad students do their work independently and then check in with their advisor and go back and work independently. And I got to actually work alongside Craig for those windows of time and see what an excellent scientist is doing moment by moment during long days in the lab. He would insist that we needed to adjust the plasma so that the density and temperature and magnetic field were just right so that we could have conditions relevant to auroral physics. And we would spend days adjusting the plasma and taking Langmuir probe measurements just so we could get maybe a half day of good data. We'd also spend hours tuning the Alfvén wave antenna that Scott built, tuning and retuning so that we could launch the Alfvén waves that we wanted. And he impressed upon me that a little bit of good data is far more valuable than a lot of mediocre data. Craig was also committed to teaching well. When I started teaching, actually the first time I taught a college lecture was in this room. I was filling in for him as a grad student, and I was pretty nervous at that point. He handed me his lecture notes, and they were covered in chalk. because he held them close while he was working this very whiteboard. And they were so detailed. They were like gold to me as I was getting started, because he wrote out word for word what he wanted to have on the board, and line by line the equations that he wanted to put on the board. And I asked him at one point, Craig, why do you write this out in such detail? You've been doing this for a while. Surely you could just get up and lecture. And he said, because the act of teaching is too important, and I owe it to my students to get it right. And that impressed upon me. That left an impression on me as I was getting started as a teacher. Two bits of Craig wisdom before I get into the science. Once I was preparing a talk and I was nervous. I didn't know exactly how to anticipate the audience that I would be speaking to. And so I wasn't sure, if I'm not sure of what the audience will be like, I don't know how to gauge the level of my talk. Will I be speaking too high or too low? And Craig's perfectly aimed bit of advice for the anxiety I had in that moment was never underestimate the joy of being in the audience of a seminar and hearing the speaker talk about something you already know. And that was perfect. That was exactly what I needed to hear. And I think about that a lot as I'm preparing talks to this day. Another thing that Craig instilled upon me is the importance of measuring things that are fundamental, yet taken for granted and have not been previously measured. So when I showed up at Iowa as a grad student, just a couple years prior, Craig had published a PRL, and he was really proud of this paper because he had measured the dispersion relation of dispersive Alfvén waves for the first time. That's something that had been taken for granted for years in the plasma and space science communities. But Craig realized that nobody had measured that. And so Craig and the Iowa collaboration went to LAPD and performed those measurements. And so there were times in my own graduate school career where I was a little fretful, thinking, I'm trying to perform measurements to measure something that people have basically always expected is going to be there. So why are we taking the time to follow this up in the lab? And Craig was, he was so principled and so adamant. Physics is an experimental science, and until it's measured, the book is not closed. And that was good encouragement for me as I was going through my grad school years. Okay, onto the science. Craig's path to the large plasma device began before the large plasma device was even constructed. And so others, I believe Torbert showed this plot earlier. Craig's PhD thesis models auroral electron time dispersion that's often seen in rocket data of electrons coming down in auroral regions. It's seen here in the 1985 rocket data that was a part of Craig's thesis. And by time dispersion of auroral electrons, Craig meant these downward slashes. In the 94 paper with Torbert, he described them as slashes. And so you see what this is showing is that higher energy electrons show up earlier in time, and then lower energy electrons are following. And Craig was attempting to model this, or he modeled this in his PhD thesis by applying an electric field parallel to the background magnetic field. And this was just in the late 80s. It was on the tail end of being a controversial idea at that point. The objection being that plasmas are so conductive that a parallel electric field would short out almost immediately. But Craig referenced two possible explanations for a parallel electric field, either something DC, electrostatic, that exists in the auroral areas, or Alfvén waves. Dispersive Alfvén waves can carry a parallel electric field. So following up on this idea of dispersive Alfvén waves, Craig performed some calculations. So the data you're seeing here is a result of calculations, not experiments, not rocket data. And Craig wanted to dive into the fundamental physics of how Alfvén waves could interact with electrons to create the type of signatures that were seen in that spectrogram on the previous slide. So Craig performed what's known as a phase space mapping calculation. And the idea of this is pretty straightforward. If you imagine a test particle and having that test particle encounter the electromagnetic fields of an Alfvén wave, then you could calculate how the velocity of that particle changes after the encounter. And Craig did that for a whole distribution of electrons. So the distribution of electrons encounters an Alfvén wave, and you ask, how did the velocity of the distribution, how did the particles get perturbed? And Craig loved this graph. This was from his 94 JGR. And Craig and I talked about how to best present this graph because I've had to present this many times. So I'll try to channel some of Craig's words here. The way that this calculation was set up is that it was a uniform plasma and there was an Alfvén wave pulse traveling through the plasma. It was a very simple pulse. It was a single sinusoidal period of an Alfvén wave. So just one sinusoidal period of an Alfvén wave traveling through uniform plasma. And the graphs that you see here are snapshots of the distribution function that were produced by his calculation. But these are snapshots, they're local snapshots. So we're looking at the distribution function at one point in space. And we're seeing the distribution function as it evolves before the wave arrives at the location where we're monitoring, several moments in time as that wave pulse is traveling by the location where we're monitoring, and then a final snapshot after the wave has passed by. And Craig's calculation found two effects. One is shown in blue. I've added some markings to Craig's graph. I hope you wouldn't mind. One is shown in blue. It's the bulk of the distribution oscillating. And so you can imagine an Alfvén wave needs to have density oscillations and current oscillations associated with it. And that's what the bulk is doing here. It moves down and then comes back. And then after the wave has gone by, the bulk is the same as it was before. The other effect that Craig found is highlighted in red. And Craig found that there's a burst of accelerated electrons traveling ahead of the wave. You'll notice this population of accelerated electrons shows up before the wave gets there. And Craig argues in this paper that electrons are reflected off the leading edge of the wave packet, like snow gets pushed out in front of a snowplow. And those electrons travel ahead of the wave packet. And therefore, it makes perfect sense that you'd see these accelerated electrons before the wave even shows up. Two things that Craig loved to point out about this graph. One is that you'll notice the distribution after the wave has gone by is missing something, right? There's this little bit of the distribution that got snipped off, and those are the electrons that were picked up and pushed ahead of the wave as it passed by the location where graphs were being drawn from, or our data is being drawn from. The second thing that Craig loved to point out about this graph is a kind of a geometrical way of thinking about this. If you look at the accelerated burst and you imagine reflecting it vertically, it matches the piece that got snipped off of the distribution. And that reflection, you need to decide, well, where are we going to reflect it over? It turns out if you reflect it over the Alfvén speed, then it falls right in place. So Craig loved to point out those couple things on this graph. Now, Craig got interested in this by looking at the time-dispersed bursts of electrons. So he extended calculations. Oops, sorry, I'm getting ahead of myself. In case I lost you on the last slide, here's an animation. There are electrons that can resonate with the wave and electrons that oscillate with the wave. And in the in the wave frame, the resonant electrons just kind of roll up the potential energy barrier and then roll back down. And in the wave frame, of course, the wave structure is stationary. But in the lab frame, the ideas that Craig was presenting was that this electron is kind of like you can imagine a ball bouncing off of a moving wall. That ball bouncing off a moving wall can actually come back to you faster. And that's what's happening here to the red electron. It is reflecting off this moving potential energy barrier, ends up traveling ahead of the wave, and it ends up traveling faster than the wave. And that was those bursts of electrons that were shown on the previous slide. Okay, now, Craig wanted to look at the time-dispersed bursts of electrons. So he extended this calculation to a dipolar magnetic field. And of course, the Alfvén speed changes as you descend, as the Alfvén wave descends into the dipolar magnetic field. And so that means the resonance condition changes as you go into the dipolar magnetic field. And the net effect of that, Craig found, was that the energy of electrons accelerated changes. And you actually get this time-dispersed burst of electrons that he saw in rocket data. And this came out of an extension of his phase space mapping calculations. He was also able to show in his calculations that slower electrons are accelerated at a higher altitude when the Alfvén wave is traveling more slowly. And then the faster electrons are accelerated at a lower altitude, and they end up overtaking the slow electrons. And they end up arriving first at your measurement platform. All right, so Craig, being somebody who wants to not only have an understanding of the fundamental physics, but also make measurements of the fundamental physics, started eyeing the large plasma device. And this is a facility at UCLA that was designed really for Alfvén wave physics. It's a premier facility to this day for studying Alfvén waves. It's 20 meters long, end to end, and so it's just a big column of plasma inside of this vacuum chamber. And it has a solenoid wrapped around it. The solenoid is formed by these purple and yellow coils. That creates a magnetic field that just runs straight left to right, or maybe right to left, I'm not sure. A solenoidal magnetic field that runs through this experiment. And the reason why it has to be big is because, as you know, typical Alfvén wavelengths are quite long. And so we were lucky in our experiments to get 1 or even 2 Alfvén wavelengths in this 20-meter long experiment. The way that Craig told the story is that he was at a meeting in 1999. It was IPELS at like a castle in Scotland or something. And he was sitting around and went up to Walter Geckelman, who at the time was the PI of the Large Plasma device, and said, Walter, you've got this machine for studying Alfvén waves in the lab. I've got an idea of how Alfvén waves are contributing to the production of auroral electrons. Can we get together and do some measurements? Because Craig valued measurements of the fundamental physics. And through that conversation, Craig became the first external user of the Large Plasma device. And the LAPD now is known as one of the bedrock foundational user facilities in the fundamental plasma physics community. There are dozens of users from around the world that come in and perform experiments on the LAPD. So Craig was a pioneer in thinking about how facilities like this could be shared. Now, Craig was so methodical in his approach to these types of experiments. He wanted to first make well-defined Alfvén waves and measure how they propagate through the experiment. And then we could shift our focus to looking at how Alfvén waves interact with electrons. So Craig, or maybe mostly Scott, built an antenna here that has 48 grid elements and 48 amplifiers that could be individually controlled. And that meant that you could tune the antenna in different ways. And the way geometrically that this antenna is laid out, that the grid elements are spaced along the X direction. And that means that you could impose different patterns along the X direction by changing the tuning of the antenna. The take-home message here is that this antenna was perfect for imposing different perpendicular wavelengths, or the same statement of that, or an equivalent statement of that, is that it was perfect for imposing different perpendicular wave numbers on the Alfvén waves that are being launched by this antenna. And there had been predictions up to this point that the phase speed of Alfvén waves would change as you vary the perpendicular wave number. And what Craig found with his measurements, Craig and the Iowa collaboration found with their measurements, is that indeed the Alfvén wave phase speed drops off as the perpendicular wave number picks up. Now, the Iowa group became experts at launching Alfvén waves with well-defined perpendicular structure. So all of a sudden, there was a realization that there were all sorts of experiments that could be run if you can define Alfvén waves well with good perpendicular structure. And so this was used to study Alfvén wave turbulence. Now, this is also sometimes called an Alfvén wave collision experiment, the idea being that 2 Alfvén waves are generated at opposite ends of the LAPD. So there's an antenna down here launching a wave, there's another antenna down there launching a wave, and they're traveling towards each other, and they're going to run through each other. And in a linear description, you would just expect waves to pass through each other and go on their merry way. But the theory of Alfvén wave turbulence says that there's a non-linearly generated third wave that shows up. And that should have a higher wave number. And so here's a representation of the results that were found. I apologize for the small axis labels. This is perpendicular Fourier space, so Kx and Ky, perpendicular to the background magnetic field. One of the parent waves, or antenna-driven waves, had structure primarily along the Kx axis. Another of the parent waves had structure primarily along the Ky axis. And then when they were running through each other, they non-linearly generated a new wave that had the sums of these 2 patterns that was created this new wave that had a higher wave number than either of the parent waves. And the lead author on the paper that came out of this, Greg Howes, said this is the fundamental building block of astrophysical plasma turbulence. While that was happening, the Iowa group was also busy developing measurements of the electron distribution function. Remember, Craig was here because he wanted to measure the acceleration of auroral electrons. And so to do that, you have to be able to measure electron distributions in the lab. And I'm jealous of the space physics people here because you can go out in space and measure particle distributions that are beautiful. It's much more difficult to measure electron distributions in the lab. The technique that was applied here with Craig and Fred Skiff and Derek Tex is an idea called wave absorption. And the idea is that if you have a small amplitude wave that's absorbed in proportion to the number of resonant electrons that are responsible for the absorption, you can infer how many electrons there are absorbing the wave if you measure how much the wave is absorbed. And by sweeping the wave across frequencies, you can actually build up an electron distribution function. So this is a technique where a diagnostic wave is used to measure the electron distribution. And in this case, the Whistler mode wave was chosen because it resonates with electrons. So this was implemented in the early 2010s, or the first results were published from this in the early 2010s. And it's shown here as a chirped interferometer. Moments of the distribution function. One of the first things that was done with this diagnostic is moments were taken of the distribution that were measured to get density and temperature. And then that was compared to well-accepted Langmuir probe results. So Langmuir probes, of course, are used all the time in lab plasmas and are generally believed to give measurements of density and temperature. And so moments of the distribution function to produce density and temperature from this new diagnostic technique were produced and compared to the Langmuir probe results and found to agree well. So this was evidence that the measurement of the distribution function, this diagnostic technique that was newly implemented at the LAPD, was giving something credible. Now, the final step in this process was to measure, to create Alfvén waves, measure the electron distribution function at the same time, and see if electrons are being resonantly accelerated, as Craig had focused on way back in his PhD thesis. And that's exactly what we ended up finding in our 2001 publication. Our experiments at the LAPD, where we were launching Alfvén waves and measuring the electron distribution, showed that electrons are accelerated by Alfvén waves in a manner that's consistent with Craig's 1994 phase space mapping calculation that I showed earlier. And the way we did that was with a field particle correlation technique. So we measured the electron distribution function, we measured the Alfvén wave fields, and we could, by correlating the two, determine which parts of the distribution were gaining net energy, which parts of the distribution were losing net energy. And that's what's shown on the graph here. So energy is on the horizontal axis. It's a signed version of electron energy. And then the field particle correlation is on the vertical axis. And you'll see that there's these regions of the distribution where the electron distribution isn't gaining any net energy. But there is, over here, something happening. And these portions of the electron distribution are gaining net energy. And it turns out those are exactly, that's the speed of the electrons that you would predict should be able to get pushed out ahead of the Alfvén wave in kind of that snowplow resonant acceleration action that Craig had showed in 1994. And finally, we had measurements of that happening right at the speeds that you would predict. So I'll close by saying Craig is recognized as being a driving force that led to today's close collaboration between lab and space plasma communities. And here's a picture of me with my thesis committee several years ago with Craig over here on the left. So thank you.
Thank you very much, Jim. All right, so next is Dr. Stephen Fuselier of Southwest Research. Probably doesn't need much introduction to this crowd, but those that don't know him.
The first one on the top.
This switch does.
The keyboard.
Yeah. Okay, I have the privilege of talking about the Tracers mission and actually Craig's involvement in that or conception of the Tracers mission. So I'm going to talk a little bit about what is the Tracers mission and basically explorers in general, and then the origin of the Tracers mission, and talk about the Trice-1 and Trice-2 rockets briefly, because they were very instrumental in the conception of the Tracers mission and the implementation. And I want to conclude with a little bit about what Craig brought to Tracers, and this is a lesson really in leadership that I think we can all take away from this from Craig. So Tracers, first off, what is it? So Tracers is a NASA Small Explorer mission. So the Explorer program, at the University of Iowa, there's no introduction needed for the Explorer program. It's the longest running NASA mission line. It started with Explorer 1, and it started here at the University of Iowa. So it's really only fitting that Craig brought back an Explorer mission to the origin of the entire mission line. In the 1990s, NASA revamped the program to return it to its roots. So the Explorer program had begun to grow in complexity and cost and duration. And in the 1990s, NASA basically devised revamped the program so that you had a small Explorer mission and a medium Explorer mission that you could propose to. And the small Explorer mission was capped at between $110 and $150 million now. That sounds like a lot. It is a lot, but I just want to remind you that JWST costs $10 billion. So you can get an idea of the magnitude of the difference in the programs. The other quantity I like to mention is that $150 million for basically a program that runs almost 10 years, but 5 to 7 years. That's every taxpayer in this country contributing $1 to the mission. And so I think you probably imagine that you probably get your dollar's worth out of this mission. And it's important to realize that, there's revamping of a program. When you write a proposal and win an Explorer, you have to thread a needle. And that's really what Tracers does. You have to, Explorer class, exciting, focused science. Think of Explorer 1. It was actually not designed to look for to discover the magnetosphere. Its original goal was to figure out the true cosmic ray flux. So get above the atmosphere of the Earth, and you would measure the true cosmic ray flux. That's of course not what happened, but that's all. That's what exploration is all about. So you do Explorer class, exciting, focused science, but you have to accomplish it on a tight, fixed budget. And so you have to not only conceive of a mission that has exciting science, but you have to have the realization that you can do that mission in the cost. And so that's what I mean by threading the needle. And yes, it is true that the mission was conceived at a dinner on a napkin, shall we say, at an AGU meeting between myself and Craig Kletzing and a couple other people. But that's really not the entire story, as you will soon see. So I'm going to have to deviate a little bit and talk about magnetic reconnection, because that's what the Tracer's mission is all about. It investigates a long-standing problem we have with magnetic reconnection. It's a problem that was identified, as you'll soon see, back in 1995, and has persisted to this day. The magnetic reconnection, so if you have magnetic fields pointing in opposite directions on a converging plasmas, they tend to annihilate each other in a region we call a diffusion region, releasing magnetic energy and heating charged particles and accelerating charged particles in the surrounding environment. It's this fast release of magnetic energy requires oppositely pointing magnetic fields to be torn apart and reattached. So you're not creating monopoles here, but you tear apart and reattach the fields, and that's the essence of the process of magnetic reconnection. It's a universal fundamental process. You can find it in astrophysical plasmas. You can find it at the Earth in two regions. They're shown on the day side. It's a subsolar region, and that's actually what Tracers focuses on, that reconnection, and also in the magnetotail. But you also can see it. It's responsible for the release of magnetic energy in solar flares and coronal mass ejections. So how does Tracers investigate reconnection? So I have never had the pleasure of watching Craig give a lecture, but I am told he was fond of demonstrations. And so I have a demonstration here, which will hopefully let you visualize the process of magnetic reconnection and particle acceleration. So this is a rubber band. There's the Earth. This is the two magnetospheric cusps. And the stretching of the rubber band represents the tension. The tension in the rubber band represents the magnetic energy that we have. So if I cut this rubber band, maybe, you can see that the rubber band snaps and actually convex over the poles. So again, there's no monopole. The convection is basically because you tied this field line now to a solar wind field line, and it's going to convect over the poles. And so that's what you see in this picture here of a magnetic field line that reconnects on the day side subsolar region and just basically convex over the pole. So if you fly a spacecraft through that structure, because you're essentially accelerating all the particles at once, the faster particles are going to go down to the ionosphere, and they actually mirror and go back up, but they will go down to the ionosphere faster than the slower particles. And so if you fly a spacecraft through there with a particle detector, you'll see, if you plotted particle energy on the vertical scale and magnetic latitude or on the horizontal scale, you would see a dispersion where you saw the fastest particles first and then slower and slower particles. Fortunately, that's not what you see. What you see, and this is actual spacecraft data from Polar, what you see is not a nice smooth dispersion. You see a series of steps, and these are called cusp-ion steps. And so the question was, why aren't you seeing a nice smooth dispersion? And the answer was that, now I can't go forward. The original interpretation of these steps was that this was temporal variations in reconnection. And so the reconnection starts, and you get the beginning of the dispersion, but then it stops, it levels out, starts again, stops, starts and stops. So temporal variations in reconnection. However, there was a famous paper in 1995, Terry Onsacker and company wrote, that showed observations from two different spacecraft going through the cusp at two separate times. And the structure that these cusp-ion steps, the evolution of those steps was inconsistent with this temporal variability picture. And in fact, the observations were consistent with spatial variability. And spatial variability is that you're cutting across different flux tubes that have different time history of reconnection. And so therefore, you see these steps as basically just cutting across different flux tubes. So now you had a quandary, because on the one hand, you had temporal variability, and there were later observations that showed that, there were cusp-ion steps that were consistent with temporal variability. And then on the other hand, you had spatial variability. And so by 1995, and the important thing about this, Craig's link to this, was that the cusp model that they used in this paper was actually created by Craig. And so by 1995, Craig had in his hands, this is 20 years before actual proposal of tracers, he had in his hands an excellent science question: is reconnection primarily, and the key word there is primarily, spatially or temporally variable? And he had a way to answer that question, which was equally important. Just put two spacecraft in the cusp, one after the other, and you'll be able to answer that. And so now the final piece of the puzzle was, could you do it on a SMEX budget? And that was critical, and that's why the TRICE rockets campaigns were so important, because they in effect showed that you could do this on a SMEX budget. So the first TRICE 1 was launched in 2007, and I hate to claim advantage over a really mishap, but the ion and the electron instruments had issues on TRICE 1, and so Craig decided that he was going to repropose those two rocket experiments, and that became TRICE 2. And he came to me and he asked if I would do the ion instrument, and then I would do the electron instrument. And so it was proposed in 2014, and that was the element, that was the second element of this key in proposing a winning Explorer mission, was that the realization from both of us, but mainly from Craig, that you could build a payload, a very simple payload, a rocket payload essentially, put it on two separate satellites now, and just repeat that rocket experiment over and over again every 95 minutes as you fly through the cusp, 3,000 times in a year. And so you had the statistics to do this question of, is it primarily spatially or temporally variable? It was just a lot of fun, actually, to put together this proposal, realizing that we had all the elements of a successful SMEX mission. You see the picture in there. This is the Andoya Space Center in December of 2018. The ubiquitous Jim LaBelle is sitting in the front there. And yeah, he does still have the same shirt on. Yes. But that was we would get up at 5 o'clock in the morning and go down to the range. We had a 4-hour launch window, and we would look at the IMF conditions from the geosynchronous satellite. From the satellites upstream at L1. And we would decide if we had the conditions right, as we needed southward IMF. I can say that got old after about the third or fourth time, but I think it was the fourth time was the charm, and we got the right conditions. We launched in 2018. We got the data back. We had extraordinary success, and this was between the proposal, which we won phase A, and the site visit that we had with NASA headquarters and the Explorer office in January of 2019. So when we went to the site visit and they said, how do you know this is going to work? We just said, here's the rocket data. We're just going to repeat this 3,000 times. And so it was really a foregone conclusion that we would win. But as you can see, it was all set up really over a period of 20 years to get the right science question, the right focus, and to realize that you can do this in a SMEX budget. So that was a successful proposal. It ultimately led to the successful TRICE-2 launches, and it proved that the Tracers mission was possible. I want to mention, though, throughout the proposal writing process and really the development of the Tracers mission, and why it really is, it's Craig's mission. We had the advantage of having some just extraordinary leadership from Craig, and this is my lesson in leadership, is that Craig knew how to get input from his team, but he also knew when to make a decision, and the respect that we had for Craig. When he made a decision, it was accepted and final, and there was no question about that. And I can tell you, all the way along in the proposal development process and in in the mission development, that every one of his decisions were the right ones. So it was an enormous privilege to work with Craig and Tracers, and this mission is going to be a fitting tribute to his insight and leadership. Thanks.
Thank you, Steve. You need to get
No,
I want the microphone. You can get your visual aids. Board the aircraft.
No, I borrowed that. The TSA would not allow me to.
Is Aria here? Aria's here. All right. Well, no, Allison was next, but if we want, let's go ahead and have Aria. Yes. Come on down, Aria. Aria was another one of Craig's students. He just flew in. I bet his arms are tired. Let's see. Okay, do you have his art here? I'll let you get.
Yes, let's hear.
Figure this out.
It's good. Can you guys hear me?
Sharing.
Well, when we're sharing the right one.
All right. Good morning, everyone. I just got in, so hey, no, I'm really happy to be here talking about Craig Kletzing. So my name is Arief Shari. I'm a former graduate student of his. I am currently an assistant research scientist working with Professor Greg House here at the University of Iowa. And Professor Craig Kletzing was my PhD advisor, and he was also an inspiration. So it's really an honor to be up here talking to you about him. I'm going to be talking about the rocket missions I got to work on, which I know some previous speakers have already talked about. I'll give it from my perspective. The satellite from which I got data to analyze for my dissertation, and the big man himself. Obviously, we know who that is by now. So that term, the big man, is kind of something Dave Hartley and I came up with. It's a really endearing term we have for him. He was a big guy in the department, and we got to work closely with him. And he was upstairs, so we'd say the big man upstairs. We'd often go to his office to try to talk to him. What he wasn't there, we could find him in Danny Crawford's office or somewhere in the building. But besides being such a big guy in the field, in the department, he was always humble and he was always down to earth, which made it great to be part of his team and be around him, really. So this is the timeline from which I knew him. I've known him a little over a decade now. And I'm not going to talk about each one of these dates, but these are basically the times that have been a big moment in my life revolving around Craig himself. So I'll start with really the first date that in March 2014, I got invited to the University of Iowa for my graduate student orientation or preview day. And that's when I went to Craig's office and he gave me a little rundown on the rocket missions that he was working on. And he tried to get me to join his team. And the final thing is that I did join his team, but in that moment I didn't know, but he lured me in with rockets. He said, we have this launch coming up in December of 2014 for the Caper mission. So I'd like for you to work in the lab that summer. Unfortunately, or I guess fortunately for my part, I was going on a 2-month travel to Peru and Brazil. And Craig, he loves traveling. So he was instantly excited about that. Where are you going? What are you going to do? So we talked about traveling from the start. So I had to decline joining his team then. But later on, I did join his team in March 2015, in my first year of graduate studies. And that's when I met Scott Bounds and Jeff Dolan and Danny Crawford and formed a good relationship with all of them, and all thanks to Craig. He introduced me to them. I got working in the lab, and in that summer, I got to do the rocket integration, do the calibration on the detectors. So I'm going to skip ahead. There's a lot of stuff that happened and we could talk about it all later offline. But in June 2019, when I was at the GEM conference in Albuquerque, New Mexico, that's when we heard that Craig won the Tracers mission. It was exciting for all of us who were around him, under him, working with him. I was super happy being a student. I mean, he's such a great guy that it was nice for us to know that he won this Tracers mission. And I was telling everyone, oh, we're going to get back to Iowa City and see banners of Craig on the side of Van Allen Hall. They weren't there, but I still think they should put up banners of his face on the side of the building. It's not too late. And then November 2020, during the thick of the pandemic, is when I virtually defended my dissertation. And Craig was leading that for me. And then in June 2022 was the last time I saw him at the GEM conference in Hawaii. And we all know, as I said, he loved to travel and he also loved Hawaii. So it was nice to see him there and hang out with him. So that's the timeline, but getting into some of the more stuff I did with them. For rockets, I started with the Caper mission, and in the summer of 2015, I got to work in the lab with Scott Bounds and Jeff Dolan doing the instrumentation and some of the calibration on the detectors. And then in summer of July 2015, Craig sent me to Walt's flight facility on the lovely island of Chincoteague in Virginia to actually put the instruments on the science payload and do a lot of our testing over there. But the flight facility is a very cool place. If you're ever on the island, it's a cool island. And the public museum for the sounding rockets is very cool to check out. So these are some photos from our integration procedures. That's Scott Bounds in the lower left picture, checking out his handiwork from when we stood up that Caper science payload. And then that's me in the shorts. I don't know if I should have been wearing shorts there, but no one said anything. So that's me with Walt, sorry, taking off the covers of some of those detectors, getting the science payload ready for one of the testing that we did on it. And then, so unfortunately, the first Caper mission had a launch vehicle failure. So I fast forward to the TRICE-2 and Caper-2 missions, which were both successful. So I had a brief interlude going into the MMS mission and doing data analysis, and Craig got me introduced into that. But after we needed to get back onto the rockets, so he got me back in the lab working with Scott Bounds and Jeff Dolan again. I always loved working in the lab. So it was a great time, and Craig was always a great PI, coming in there, seeing what we're doing, and then taking us all to Andøya Space Center in Norway for the rocket launch. This is in December 2018. That's Scott Bounds on the left, Craig in the middle, and then Professor LaBelle on the right side in the launch control room, looking at whether we have the science conditions and whether they wanted to launch. That day we did not launch, but then fast forward a few days later and we did launch. And this is a video I'm going to play from when Craig gave the okay to do the launch. So there's no volume really. He was just walking around checking out the conditions. And this is actually one of the 2 times I've seen him be nervous. The other time was when he gave the tracers presentation. But he was a little nervous. There's a lot riding on this. So he made the right call to launch. They did the countdown timer and you could see they held it at T-3 minutes. And this is when most of us ran outside to see the actual launch, but Craig had to stay inside to watch to make sure everything's working properly from inside the control room. So going outside was an amazing experience. This is one of the best things I've ever seen in my life, to see a rocket launch, and then not just one rocket launch, because it was a tandem mission. We got to see 2 of them. So we're standing, I would say, roughly 200 yards, maybe more, away from the sounding rocket. So I hope the volume is really loud, because it was really loud over there. So this is a video. So you hear some car alarms in the video too. So when the rocket takes off, the first thing you see is the light travels a lot faster than sound, obviously. It just washes over you, and the kick of the exhaust hits you, and it was very strong. It took me off guard, and I was thinking, are we safe standing here? But obviously the Andøya Space Center people know what they're doing. We were at a safe distance. So I was really primed for the second rocket launch. And then a few minutes later, we had the TRICE-2 low flyer take off. And in this video, if you look on the right side, once the rocket launches, you'll see the exhaust from the first rocket. Yeah, we were excited. So that was probably one of the coolest things I've done in my life. Who gets to launch rockets into the auroras, I know some people in here get to do that, so that's very cool. And then a few minutes after the launch, or a few seconds, my memory might be a little fuzzy, you see the Talos initial booster fall into the ocean a few hundred yards offshore. So it was all around a fascinating experience, and I really thank Craig for sending me to Andøya Space Center, being part of his team, getting to do these rocket launches. So those were the rockets. Now getting into the satellites. Craig was part of the MMS team, and he got me involved after the first Caper mission had that launch vehicle failure. I got involved in the magnetospheric multiscale mission to do some data analysis on this. And the NLS mission is 4 identically instrumented spacecraft orbiting Earth in a highly elliptical orbit. It goes through the Earth's magnetosphere into the magnetosheath and into the pristine solar wind. And the main goals were to look at magnetic reconnection and turbulence. And Craig was involved in the Fields instrument team. So him and Scott Bounds were looking at were working on the electron drift instrument, and they developed this instrument. It's a functioning part of the spacecraft. Consequently, I didn't look at any data from the EDI. I used magnetic field data from the fluxgate magnetometers and electric field data from the electric field double probes, but Craig knew the people part of this team, so he got me involved with this group, with the MMS group, and he really got me involved in looking at the particle distribution data from the Fast Plasma Investigation, so FPI, and the PI is Craig Pollock. So I started working with the MMS team in February 2016. He sent me to Goddard to meet the team and to learn more about the instruments. And at that point, Craig Pollock was transitioning to retirement. So I met Barbara Giles. She was taking over the team. And that's also where I met Scott Bordson, who I keep in touch with, and we still work together. So I was looking also at electron and ion data from the Fast Plasma Investigation. And I'm going to get into some of the technical stuff, but hopefully not too much into the weeds. So these are electrostatic analyzers that are called top hat electrostatic analyzers. And if you look at the bottom left cross-section view, you see there's a little elevated part of the electrostatic analyzer. And that's why it's called a top hat. That's where the particles enter. And Craig would always tell me it's like a top hat. So he would do that motion, and it stuck in my head being in his office and him explaining that to me. So these are top hat style electrostatic analyzers. They're back to back, and there's 4 sets of 2 of them around the spacecraft. And that allows them to sweep in the azimuthal direction, 360 degrees, and full sky view for electrons in 30 milliseconds and ions in 150 milliseconds. And that allows us to look at kinetic physics in space plasmas. And while I was learning about how these detectors work, Greg was telling me you got to learn about the geometric factors. So I don't know if you could see this, but this is his handwriting. He gave me his personal notebook from 8 June 1987, 6 days before I was born. And I told him that. And then he said, oh, well, now you know how I am. I just thought it was cool that he was working on these rocket missions when I was born. So he gave me his notebook. He said, go copy this, go make a photocopy. I made a photocopy, printed it out, glued it into my own lab notebook. And then as I was reading it, I see it says, in the first line on the upper left, it says from Roy's book. And I'm guessing that's Professor Roy Torbert. So he got it from his advisor, and now I got it from my advisor. So now it lives in my notebook. So after learning about all of this stuff, about how the Fields instruments work, how the particle detectors work, I went on and did some science with a lot of help from Craig. Now, this is probably the most sciencey slide I have. So having the fields and the particle data, I use the field particle correlation technique, which basically characterizes the net energy transfer from field fluctuations to the particles or vice versa. So the energy could go back and forth between the fields and particles. And it's a technique developed by Professor Klein, who was a former graduate student here working with Greg and Professor House. And the technique was also developed by Professor House. So basically, we have the Maxwell-Boltzmann equation, which describes how the particles change in time due to the forces acting on them. And we ignore collisions because it's a collisionless space plasma. If you multiply that by 1/2 mv squared and you integrate it over all velocity space, you get the Joule heating. So how much energy is transferred between the fields and the particles back and forth. But the point of the field particle correlation technique is to not integrate over all velocity space. So you get to retain the velocity space information and time information in the electric field and the distribution measurements as well. So due to the dot product we have in there, we break up the E dot grad F term, And I'm sorry if this is too technical, but this is the only science slide, so bear with me. So that E dot grad F term, we break that up into parallel and perpendicular components. And the parallel correlation is related to lambda damping and other things, but we focus on lambda damping. And then the perpendicular term is related to cyclotron resonance. So we spent a majority of the time developing this technique on actual spacecraft data, looking at the parallel term. And in the upper right-hand corner is a publication we had in 2021 in JGR, where we analyzed 20 intervals. We found evidence of electron lambda damping in 19 of those 20 intervals. So panel C in the upper right-hand corner is the real kicker. Where there's red, it means the particles are gaining energy from the fields, and where it's blue, it means the particles are giving up energy to the fields. Now, we integrated that over all space, and we get the Joule heating, as I mentioned. So we actually have this number that we can compare to the turbulent cascade rate, and we found that electron lambda damping accounts for about 30% of the total cascade rate in half of those intervals. So there's a lot of intervals that have evidence of electron lambda damping, but they don't dissipate a lot of energy. So for this current work that has just been accepted and is going through editorial work to get published, we looked at some of those intervals, and we looked at interval, we labeled it O2 in this one. In panel A in the bottom, in the middle row, we have the power spectral density of the magnetic fields, where between the two vertical black lines, we have excess power in the fields near the ion cyclotron frequency. And then in panel C, in that middle row, we look at the polarization of the magnetic fields, and we see a left-hand polarized wave indicating a left-handed ion cyclotron wave. And we do the perpendicular field particle correlation, which is panel B. And this has the perpendicular and parallel velocity space. And it's compared to panel A in the bottom row, which is a simulation of ion cyclotron damping. So we saw evidence of ion cyclotron damping in this turbulent magnetosheath interval. And it's great work, and I'm excited for it to be released soon. There's a lot more work that we showed that this was ion cyclotron damping. This is just a little touch of it. But it'll be out soon. And for both of these papers, Craig was an instrumental part of understanding the science, understanding the data, and getting it written up, really. And he was a busy person, so it was very nice of him to spend the time to talk to me about all this stuff. So his legacy, this is from the GEM 2016 meeting. That's me on the far right, and then Dave Hartley in the white shirt, and Sebastian De Pasquale from who is also a graduate student of Craig's, and then Suzanne Smith in the yellow, who was at Goddard, graduate student, and then her sister Kimberly. But with Dave and Sebastian, we're still friends. We met in the office that Craig put us in. We still keep in touch. We still work together, and that's kind of the legacy I see. But there's also plenty of other research scientists, plenty of other professors, plenty of other postdocs that Craig's worked with and made a difference in their lives. And he had us all together. He had us all make friends together, and really put people in contact with each other and connection with everyone. So as you guys know, he was always a lively person. He was always full of energy, and he wanted everyone to work together. Is like a mutual, thrive off of each other's energy. He was a bon vivant. It was great being around him. And then I saw this recently, and it made me super happy. This is from the Iowa Now digital magazine, and it's the electronics box for the Tracers mission, and it says in memory of Craig Kletzing. And the best part is that purple guitar pick that's embedded in there. Besides traveling and physics, Craig loved music. He played in several local bands around Iowa City, and I know that he would be happy to see that guitar pick there. And if he was around, he would probably want to put one himself. So it's very cool. Whoever thought of that idea, kudos to you. That's awesome. So it's been a pleasure talking about Craig and the work I've done with him. And it's been a pleasure being part of his research group. And thank you guys for listening to me talk about him.
Okay. Maybe. Yeah, thanks, Aria. By the way, that is one of Craig's guitar picks that is on there. It is one of his picks, yes. And thanks for the rocket launch videos. Those never get old. Okay, so our final speaker, and then we'll have some closing remarks. Allison Janes, colleague here at Iowa.
Yeah.
Good.
Thanks. Gotta get my jacket on to look smart, just like Craig would do for an audience this size. Okay, so I don't have any slides, actually. I just have this picture. And I was going to talk a little bit, and then I'm going to let a couple other people talk as well. So Craig was a very rare type of person and a very rare type of scientist. He was, I described him as this multi-hyphenate person. You know, he was a scientist and a researcher, an experimentalist, but he was also a mentor, a colleague, a friend, a partner, a musician. All of these things he excelled at, and don't know how he really did that, but it was amazing to watch and to know him. I first arrived at Iowa in 2017, and by the way, I don't know, maybe not everyone realizes how much Craig has shaped my career and shaped me as a person. He's the one who actually called me up and told me to apply to this job at Iowa. And I said, I don't know, I don't think I'm ready for it. And he was like, no, you should apply. And when I got here, he was dedicated to me, my faculty mentor, and we co-taught together for the first semester I was here. And just that story that Dave had about going to his office and seeing if he was there, and sometimes he'd be there, and sometimes his door would be open and he wouldn't be there. And I think equal times Craig would come down to my office and my door would be open and I wouldn't be there, or I would be with a student and I would see him in the background trying to get my attention. You know, so he was really committed to my success, and really just changed me as a person in so many ways. But we first taught together when I arrived in this very lecture hall. We did the Intro to Physics for Engineers class. And when I was telling everyone what I was teaching for the first semester here, they were like, oh, that's a tricky one. Like that, you know, nobody really liked to teach that Intro to Physics for Engineers because engineers are difficult, right? We all know that. But Craig really liked to teach it. He actually genuinely liked that course. And you know, that passion that he had for teaching, and specifically for that course, that translated to me. And so now this is one of my favorite courses to teach at the University of Iowa, is this Physics for Engineers. Like everything that he was passionate about, science, food, music, travel, that was always something that you cared about by proximity, right? If you were around him, you started to care about those things too. Except Costco. He never got me on board with Costco. But so I loved this course, right? He loved it, so I loved it. And that's kind of how it worked with Craig. You know, with Craig, I think passion was a contagious quality. So that's one of the things that endeared all of us to him so much was that passion. So he cared so much about trying to make these students just get a little more enthusiastic about physics than they were before. And the way he would do that was things like bring in his electric guitar and play for the students. And they just loved it. They went crazy for that. You know, here's this guy with a ponytail and an electric guitar who's also a world-renowned physicist and does rockets and satellites. And those engineers just hooked into that kind of thing. And I learned that from him. And that's what I did when I taught that class on my own later on. And it just all came from him. You know, sorry. So, you know, that value that he had in his mind of like how to teach students, how to interact with students, that is what he instilled in me. So here's a story. One time we were in his office, and this is when we were co-teaching the class, and a student came in and said, okay, Professor Kletzing, Professor James, I got to tell you something. We have a copy of the solutions manual. Someone has a copy of the solutions manual for your physics book. And there's some students that are going through and doing all of the problems in the solutions manual. And they've got the answers right there, and they're working them out, and they're doing each and every problem just to try to cheat on the exam. And Craig said, all right, let me get this straight. So there's a group of students who are going through every chapter and practicing hundreds of physics problems in advance of my exam. That's not cheating, that's studying. And he was like, go do it too. You get a copy of that book and do it too. So he just had this amazing energy, and the responses that he would give to the students were fantastic. He had so much respect for them, and in turn, they had so much respect for him. I caught his enthusiasm so much that when I was teaching Intro to Physics for Engineers throughout the years, I had actually converted a few of those engineers over to physics majors. And I know Craig did as well when he was teaching. So it was a privilege to be able to pass my enthusiasm on to others, like he passed on to me and so many students as well. Okay, so then the last thing that I want to say is when the Tracers project was coming together, Craig came down to my office one day and was like, hey, I've got this idea for the student option, the student enhancement option, which is a sounding rocket that would be kind of led by students and built by students. I know you really care about this stuff, so will you lead that for me? And I said, sure, of course, I would love to. And we worked on that proposal together, and you know, it was a privilege, and it is a privilege to be leading that project today. Some of the students working on that are in this room right now. And a couple of weeks before he passed, you know, I'd go visit him and spend time with him, and he was still asking about that student project. You know, even at the very end, he was wondering how that was going and when that was going to get started and all the cool stuff that was going to come out of that. So, you know, that core of him was there all along, and really, really respect that about him. I wanted to hand it over to a few of Craig's former students and mentees, because you know, I taught with Craig, but I was never taught by Craig. So I think their words are a little more important. And this is something that Craig did many times, is he ceded the floor to other people to let their words shine instead of his own. So I wanted to bring up Steve and Aria, Dave, Sebastian, and Connor. Yeah, there you are. So please come on up, and they have a few words to say each.
Just the mic here. All right, so sorry if I'm a little bit hoarse. I'm Steve Kepler. I'm a professor at Clemson University in South Carolina, and I was Craig's student from 2006 to 2013. So Allison asked me to make a couple of comments, and I wrote a few things down. A lot of you have heard all this already. So, I mean, he was generous with his time. Towards the end, one thing with me was I was in his office, I felt like almost every day as I was finishing up my dissertation. You'd think the student who's finishing up his dissertation and going out the door would be the exact opposite. But he helped me a lot with some of the modeling, which I felt like I was kind of leading it, but he was giving me good advice. The advice was a major thing I appreciated with Craig. Always gave really good advice. Craig also had a certain vernacular and certain vocabulary. There was, what I told Allison were Craigisms. Bang it out was one of them. So one of the other ones was, he told me, like, you know, I asked him at one point about interacting with, you know, certain intimidating scientific characters, you know, like Phil Erickson or John Bennell, for example. And he told me, you know, people put their leg in or put their pants on one leg at a time. So, I mean, just advice like this that, you know, it sort of puts everybody on the same playing field. Another piece of advice I got was, you know, that I was moving to California. I lived in the Bay for a few years, and he told me, you know, you can spend a lot of time wasting your life in traffic. And it turned out my wife and I actually did make the good decision of living fairly close to where I worked. I could bike or walk, which was a great idea. I have stories about bad traffic. One of the other things, I'll mention a couple of other brief things. One of the things was Craig also had a lot of professionalism. That's one thing I've actually not heard. You'll notice here that I'm in my teaching getup here, complete with tie and everything. I actually wear this when I teach. I'm sure Jim wears the tie when he teaches. Craig, everybody was mentioning the jeans. I always remember him wearing a tie, and he once told me it kind of sets a tone in a class, which is one of the reasons why I do it, because it sort of sets a professionalism, it sets a tone. The other thing that I really liked about Craig personally was that he also had a life outside of physics and outside of work. And, you know, one thing that he did have was a good marriage. It was clear that he had a good marriage. You know, obviously Hawaii, the rock band, the food. He also liked to roast his own coffee beans. I haven't heard that mentioned yet. You know, all in all, he just was a great person to be around. I'll also just end by making kind of one comment that Allison and I didn't mention this in my email to you. Allison and I have kind of came up at the same time at different places. And, you know, I could tell that when Craig had asked you to apply here, I figured it was an inside job, so you were probably going to get the job. But I think Allison has had excellent mentorship from Craig. I sort of got it early on, and I've gotten great mentorship at Clemson, but she's gotten, I think, great mentorship and is well on her way to having a very, very successful career, I think, in part because of Craig and his influence. So she's a testament to hopefully the next generation of really outstanding physicists in our field. So I'll pass the mic over.
All right, this is Ari again. I know you guys just heard from me. So Allison asked us to speak about him, and I wrote it all out. I thought she was going to read it on our behalf. So I'm going to read it verbatim. So Craig was my PhD advisor from March 2015 to December 2020. Under his mentorship, I gained experience in instrumentation and data analysis aspects of experimental physics. As an advisor, Craig was generous with his time, always willing to answer questions and help me in understanding any problem that had vexed me. Anytime his office door was open, it was an invitation for his graduate students, postdocs, and research scientists to step in and have a discussion on any topic, often ranging from traveling to music and, of course, to space physics. He was patient with the novices, such as myself, and worked out ideas in such a clear manner that made his years of expertise quite apparent. I would never hesitate to ask Craig questions, as he was always welcoming, and despite the massive demands on his time, he always made time for those who sought his help. His words were enlightening and oftentimes entertaining. I would say his advising style was laissez-faire. He would let me work on my research at my own pace, but would let us know when we had hard deadlines for work in the lab. And one thing that Stephen said that Craig said about people, that everyone puts their pants on one leg at a time. So when he won the Tracer's mission, I went to his office first thing when I got back from gym, and I was like, "Congrats, Craig! That's so awesome." And then he said that about himself. It's like, I still put my pants on one leg at a time.
So hello, Dave again. There was a few things that I didn't mention in my talk earlier. And I think I've shared an office with Connor, Sebastian, and Aria, and I'm fairly certain it's the same office that Steve was in as well. So that's kind of the link up here. And I said earlier that Craig was could be, because he was so busy, whenever he came into our office, it was kind of this thing where we'd all have questions for him about each of our individual projects. And one thing that always amazed me about Craig was he could just go from one project, answer detailed questions from one of us, go to the next person who was firing out these detailed questions. And I don't know about you, but whenever I'm switching projects, it takes me some time to kind of get back up to speed on each thing, but that didn't seem to be an issue for Craig. And yeah, that's something that I always thought was incredible to see. And yeah, kind of another different aspect about the way Craig was as a mentor was he was always interested in you pursuing the things that were interesting to you. Even when you sort of, as a postdoc kind of coming up with my first proposal ideas, he was like, oh, I've got a ton of them if you need them, but you should do what you're interested in. And of course he'd, guide you down certain paths, but he was always kind of really keen for that initial seed of an idea to come from you and for it to be something that you were truly interested in finding out. And that's something that I really appreciated from him as a mentor.
Thank you. So like Aria introduced, I'm Sebastian Di Pasquale. I shared an office with these other two. From around 2013 to 2018, I worked with Craig on the Van Allen probes mission. And something that I remember from my time here at Iowa was that during my defense, after a couple hours of discussion with my thesis committee, going through the appendices and asking why I didn't want to write extra to put them into a chapter of my thesis and maybe expand and spend more time in the summer writing that work. It was either Steve Spangler or Don Gurnett who asked me, so you worked on the Van Allen probes mission, you did all this data analysis and stuff, and Jeremy Faden helped you come up with this automated algorithm to analyze the upper hybrid resonance for the spectra. Why didn't you look at machine learning or try these other algorithms and things like that? And Craig jumped in and he said, yes, but he's graduating. So he didn't go down that path. Unfortunately, after a series of maybe questionable decisions, I actually landed in Oak Ridge and I'm working now in fusion energy and somehow found myself working on machine learning again. So, we'll see where that turns out, but I'm happy to kind of return the orbit to pass through here in Iowa. And maybe that's because I never took a class with Craig. Though I'm sure that I had heard enough of his lectures and office hours echoing through the halls to have learned something. So sure, we had talked about research some, but inevitably after about an hour or two or three of discussion, Craig would weave in interesting ways to think about completely new and unrelated physics problems to the research that I was looking at, or bring up maybe many of the people and places that he was going to see. Craig was a person that was always on the move, and that's something that I really looked up to in my time here. One of the very first things, though, that I realized while traveling on business trips with the Kletzing entourage was that not having TSA pre-check was a terrible mistake. And I saw Craig, then Scott, then George, and some of the others blaze past me in Baltimore through the express line of security, having only arrived maybe 15 minutes before our flight was scheduled to leave. The thing is, though, I never felt left behind, but rather that Craig had allowed me to find my own way, my own path through science. And never alone, as we'd always end up together again, meeting up on the other side. And I think through Craig, I learned that being a physicist, hauling your suitcase around, was more than just a profession. Rather, it was a craft that he really mastered with a certain sense of style. On each of the scientific conferences and missions meetings that I attended with Craig, he made it a point to introduce me to each and every one of the members of the team before quickly wandering off so that I'd have to fend for myself. I remember standing outside on the steps of the church next to Van Allen Hall with some 50 other scientists in an oddly well-coordinated family photo. Afterwards, Craig came over laughing. He said, "Look, we've got your mugshot. You can't quit now." And that was encouragement, actually, to keep working and finish my thesis. And I think Craig's passion for physics, sometimes surprising, sometimes moving as well, hit home an important lesson. You're a part of a community now, and there's always something more to learn in science or in life from everyone else, for we all had our own hand in the craft. Done with coursework, I thought, nope. Craig jumped in to encourage me to take quantum electrodynamics for some reason, because he thought it was a really beautiful theory and worthwhile to learn. So there were always more things that Craig was encouraging me to do, whether it was to take programming class, QED, or even to work on a graduate certificate in college teaching. As many of the others have mentioned here, Craig was an incredible educator, and he shared that passion for instruction through everyone in the community, including the high school physics organization of the state of Iowa, as far as I understand. As a teacher to me, Craig led by example, offering up old papers and a well-worn copy of numerical recipes for me to dig through. He also had another word to say on absolutely any subject, darting in and out of our shared office, talking to me and seemingly everyone inside or outside. In my time at Iowa, I've come away with a great appreciation that plasma physics and its physicists are this awe-inspiring phenomena that can be seen in the late hours of the evening after twilight, and also can be heard in the early morning hours after dawn, not just read about while pouring through textbooks just to graduate. Craig shared with me these words of wisdom. You can break an experiment, but you can't break software, which I took to mean cut your code twice, cut it 3 times, endless times, until you can measure once. And that's the way it was with my dissertation. Craig, who was seemingly hands-off, flying now through loose pages with a blue pen like a composer. You didn't need to get it right the first time, but you should do it right in the end. And Craig always made time in my research to work through things with me the right way. Practice was part of the art. Musician, mentor, teacher, and friend, Craig was a true master of his craft and dear to us all.
Thank you for those incredibly kind words. I think that's a good testament to him. Hi, I'm Connor Feltman. I was Craig's final grad student before his passing in August of last year, and wanted to talk in the same vein as Aria. I have the daunting task of compiling all my experiences with him into a few short words, so I've written something I'd like to talk about. Now, before I go talking, I'd like to point out that I inherited the beautiful office that these gentlemen also worked through, and I felt came in at the end point of many of them. So I didn't really, I was a new grad student, new blood, and these were the old guard kind of taking off their own career. So what I say that is concurrent with them is a good scientific data point, because I independently found these same things that you'll hear that they talked about. So I came to know Craig as an advisor when he offered me a research position after I taught one of his introductory physics courses, where he regularly held meetings with his TAs just for his discussion classes, and we talk about whatever came to our mind. And he must have liked what I had to say, so he offered me a research position that next summer, and I had no idea who this man was. And he's like, "Yeah, come work with me." And I was no idea how lucky I was, and I said, "I'll think about it." Came back the next day and said, "Yeah, let's get working." So before I go on, I did want to say that one of the final things Craig did when we were doing research together was just look at my data. And with all of his wisdom, he looked at this tiny little portion that I had no clue what was going on. And he just said, "Yeah, I think this proves out one of these theories that I had been working on with actually Li Jin Chen. And I've been working on that problem for the last 3+ years and will be the center of my dissertation." So his work is still being done by his students just from one comment. So he was not the the advisor I thought he would be. A meeting that started with calibrating magnetometer data would turn into conversations about where to get the best burrito, and we would wrap up about talking about theoretical nuclear doomsday scenarios. Something he apparently was an expert in everything, and he seemed to have insider knowledge to anything we discussed. Some of the little idiosyncrasies that I particularly remember about him is that his email and pager was basically a song in the background whenever we were in meetings. It would just be constantly ringing, or how whenever he was talking or explaining something, he would toss his glasses on his desk and then 10 seconds later pick them back up and then toss them on his desk again. And it would, I don't know, it was just his thing. And in particular, the one thing I could never get my eyes off of was this bottle of Cholula that was on his desk. Now, if you don't know, Cholula was red. It's supposed to be red. And when I go in his office, I think it was green. And when I told him that, I said, "Craig, I think that bottle of Cholula is bad. And it's green. And I think it was last year that it turned green." He was a very busy man. So it's frankly a difficult problem to tell you what he was and how inspiring he was. So I thought I'd let Craig do it, as he was as a mentor. In his own words from the 39th Iowa presidential lecture, he described himself as a light touch mentor who liked to develop students so that they think for themselves, that only a push here and there was sometimes necessary. My opinion, I think this shows his humility, because he did a lot more for his students than just light touches here and there. He was larger than life, and trusting him was easy because even if he made a mistake, it never felt like he did. He did have bottomless patience for his students. He was quick to forgive mistakes. I know this because I tested this characteristic revision after revision after revision of my work, which he read even though he was busy with tracers. It is true he was not much of a handholder. He preferred to treat his students with respect as a peer. He gave his students the time and space to develop their own ideas, and he didn't want to interfere with the growing pains that are required to become a physicist. And as everyone has mentioned, he was rigorous and self-disciplined when problem solving, and he expected it from those around him. It was not enough to be able to use the tools to get the result you wanted. You had to understand what you were doing and convince him you understood what you were doing. So I hope I don't speak for all of us, but maybe some ways I do, that the true lessons I learned about Craig were not really about physics. I learned lessons about physics, but during our meetings, I rarely recalled the exact words he used or the math derivations of the physics. The lessons I truly internalized were all about character, discipline in your craft, dedication to your team, intellectual honesty, and expecting that from those around you. He had a way of handling ideas he didn't agree with grace and character. He never wrote these lessons down, and frankly, they were taught just by him being himself. He showed us how to handle tough situations with confidence, how important it was to live a multidimensional life beyond your career, and how to actually use that to engage with your peers. His vast knowledge of science and culture was used to build others up, and were never to bolster his own ego. It was the example he set as a human being and the standards he put upon himself that I remember the most. And these are the things that I use to inspire myself to be a better scientist. So I'll wrap up by saying that not a day goes by in my work that I don't ask myself, what would Craig think about this? Or, how would he tackle this situation? And what would he say here and there? And I hope this is one of the greatest compliments I can give to any mentor, which is that I want to follow your example. So thank you.
Dr. Miles has a few closing comments and is going to give us a little bit of the order of the rest of the day. Good.
Closing would be the one. I'll work on that.
Perfect. So I'm David Miles. I'm another of the faculty here in physics and astronomy. I think it falls to me to close out the symposium. So what I wanted to do is tell sort of one more anecdote about Craig. I think it's much in the spirit that everyone else has been today. So I came to the department in 2017. One of the things that was different about my situation was I am Canadian. I came here from Canada. So when I arrived, I really didn't know the scientific community in the US, and I really didn't have good contacts within NASA. And so I met Craig when I arrived, and true to his character, he immediately set about trying to make connections, trying to open doors, trying to get me on a rocket. As an experimenter, the network, the people really enable you to do what you want to do. So you've heard a lot about tracers. It's a large mission, and it's an explorer's mission. It's led by a PI. When you get awarded one of these, you get what Craig described as a victory lap. So when Tracers was awarded, you get really an entourage that comes from NASA. You get the administrator, you get the head of the Science Mission Directorate, you get the head of heliophysics, and you get a chance to sort of show them around, show them your work, and really take credit for the success getting this project funded. So what Craig did, because I think you've heard here that he was very generous with his time, he was like, yeah, we got tracers. That's great. We'll do some stuff. But what if we carved out a big block of time and you could tell NASA about your work, even though you're not actually part of the project, but, we'll just make it happen. So here we are, and this is Craig. He's talking to all of these, very busy and important people from NASA and various other places in front of news organizations. And he's like, okay, so he does his spiel, and he's like, okay, now we're going to give you Dave, and Dave's going to tell you about his research. So Craig was generous with his time, and here I am, in fact, wearing the same suit, doing my hand waving in the dog and pony show, explaining my research. He was, in fact, so generous with his time that I overran the time that Craig had, the time that Craig had allotted me, and then the time that the entire tour group was supposed to go other places in the building. We, in fact, never left the room because of Craig's generosity with his time. And fortunately for me, and really this is the seminal event that sort of really started my career here, this dog and pony show was so successful that we were able to basically add me as an extra instrument that had never been part of the original Tracers proposal. So without Craig, without his generosity and his incessant ability to give his time to help other people, I would never have been part of the project. Later, as the project proceeded, after Craig became ill, he asked me to basically be his deputy to help try to keep the project moving. And I would want to comment that Craig left a strong impact on many, many people. And as Craig got sick, there was an enormous groundswell from all the people he knew, all the people working his project, that we had to make Craig's mission a success. We had to carry it forward, we had to deliver it, and we had to see it on orbit. So truly, I mean, I think one of the things that you can recognize about the impact that Craig left was how many people rose to the occasion to make his last mission a success. So Aria showed this. I just wanted to highlight it because I think it was a wonderful idea from people who knew Craig. I really like the idea that a little bit of Craig's curiosity will go to space one more time in the form of not one, but in fact 2 guitar picks. There's one on each of the 2 instrument packages for the 2 satellites. Because we do have some NASA visitors in the office or in the auditorium, I will note that we actually did this properly. We did all of the paperwork. We did all of the studies. This is an official part of the build record, and it fulfills all the requirements for spaceflight. For those that are interested, we're fortunate enough by timing that the Tracers hardware, the actual satellite instruments and the main electronics box, which is what this is, are still in Van Allen Hall. A couple of weeks ago, or weeks from now, they will move to California to go onto the satellite. So there is a tour available starting at 2 o'clock today, where if you go to basically the antechamber or the lobby outside, we're going to have grad students take groups around the universe or around Van Allen Hall to see some of the laboratories and to see the flight hardware. But it was very special to me that all of the people that Craig knew, that Craig worked with, all came together, not only to make his mission successful, but also to sort of let him go to space one more time. So there are a couple of things left today that I'm hoping you will join us with. The first is we would really like to take a group picture. So immediately when we finish now, if people could go out the back doors, outside, and then turn left, I'd really like to gather together to take a group picture for the people who are here today. If you are interested, if you come back at 2 p.m., again to the lobby, we will have students bring groups through the building to see the labs, see the hardware. And then there is a reception tonight from 5:30 to 8:30. It is not here. It's at a place called the Old Brick. It's about a 10-minute walk. And I'm just going to leave this up so that people know where they could go tonight. So on behalf of everyone you've heard from, Craig's friends and his colleagues, thank you for coming to the symposium. It was wonderful to have a chance to sort of hear about many things that he did and people that he touched that I didn't know about. And I hope now that you'll join us outside for a group picture. So thank you.